So I wanted to start out with an introduction to the Go language itself. Now I know that this is much storied territory, but I have to start somewhere, and this is going to serve as a stepping off point for us to go through a survey of the entire Go language, as well as hitting some of the key libraries along the way. So the first thing that we need to know is that Go was created by a small team within Google, and that team was made up of Robert Griesemer, Rob Pike, and Ken Thompson. Now these guys have been around the software industry for a little while. For example, Ken designed and implemented the first Unix operating system, as well as had a key role in the development of Unicode. So when these guys got together and decided that they wanted to create a language, we had a lot of talent in the room as soon as these guys got together. But one of the questions that we need to understand is why create a new language at all? Well, to understand that, we have to look at the languages that are common inside of Google. And at the time that Go was being designed, there were really three languages that were key. The first is Python, then Java, and then C and C++. Now each of these languages in and of itself is very powerful. However, the Go designers started to recognize that there were some limitations that Google was running into that might not be able to be fixed given the history and the designs of the existing languages. So for example, when we look at Python, Python is very easy to use, but it's an interpreted language, and so it can be a little bit difficult to run applications at Google scale that are based on Python. It can certainly happen, but that is one of the challenges that you can run into in very large Python implementations. Java is very quick, but its type system has become increasingly complex over time. Now this is a natural trend that a lot of languages go through. They start out very simple, but as additional use cases and additional features are layered into the language, it becomes increasingly more difficult to navigate things. C and C++ is quick as well, however, it suffers from a complex type system, and additionally, its compile times are notoriously slow. Now, the type system has been receiving a lot of attention lately in the C and C++ communities. However, they still have the burden of needing to manage all that legacy code. And so, similar to Java, it's very difficult for them to move past the history that they have because C++ applications written 10 years ago still need to compile today. And those slow compile times are another legacy issue that C and C++ have inherited as well. When C and C++ were designed, computers had nowhere near as much memory as they do today. So the decision was made to optimize the compilers to use a minimum amount of memory, and one of the compromises that brought about was the compile times can be a little bit sluggish. In addition, all three of these languages were created in a time where multi-threaded applications were extremely rare. Almost every application that was created really had to focus on a single thread at a time. So concurrency patterns built into these languages are patched in at best. And so working in highly parallel, highly concurrent applications like Google often runs into can be a little bit challenging when working in these three languages. So, enter Go. What does Go bring to the party in order to address some of these concerns? Well, the first thing that we need to understand is Go is a strong and statically typed language. So it inherits that same feature set from Java and C++. So what do we mean by strong and statically typed? Well, strong typing means that the type of a variable cannot change over time. So when you declare a variable a to hold an integer, it's always going to hold an integer. You can't put a boolean in it, you can't put a string in it. And static typing means that all of those variables have to be defined at compile time. Now, are there ways around that? Yes, Go does have features that allow you to get around its type system, but 99% of the time you're going to be living in a world that's strong and statically typed and getting all the benefits that come with that. Now, if you come from languages such as Java, then you might be a little concerned that strong and statically typed languages tend to be a little bit verbose. Well, we'll see as we get into some Go syntax how there's been a lot of effort taken to make the compiler do as much work to understand what you're talking about with a variable, so you don't have to explain to the compiler every time what your variable types and things like that are. In addition, Go, like a lot of recent languages, has a strong focus on the community that's supporting it. Just because Go is an excellent language does not guarantee success, because there are so many languages out there that it can become difficult for a new developer to ramp up on any one. As a result, there's a strong community built up around Go that's really focused on making sure that the Go language keeps moving forward and that new developers have as easy a time as possible ramping up onto the language. So what are some of the key features of the language itself? One of the first and I would argue most important features that Go has is a recognition that simplicity is a feature. So as we go through and start learning about the Go language, you're going to run into some features and you're going to ask yourself, well, why doesn't this exist? Or why don't we have that feature? And a lot of the reasons come back to this feature. there's a recognition that if the Go language recognizes simplicity is important, then that means that we're going to have to decide to leave out some other features that might be very useful but would add complexity to the language. Additionally, Go focuses on extremely fast compile times. A lot of modern development environments to write code fast, to build it fast, and to test it fast, and get feedback back to the developer as quick as possible. Well, if you've got a 45-minute compile time, it breaks that cycle, and developers have a very hard time staying in that design, build, test loop. And so Go focuses on keeping those compile times down, even though it's going to yield us fully compiled binaries at the end. Go is a garbage collected language, which means that you're not going to have to manage your own memory. Now, you can manage your own memory, but by and large, the Go runtime is going to manage that for you. And the reason for that gets back to the simplicity argument. There is a recognition that a garbage collected language does have challenges when dealing with certain use cases. For example, real-time trading systems for stock market systems have a very hard time when you're dealing with garbage collection. However, the advantages on the developer of not having to manage their own memory all the time were deemed to be more important. Now, that doesn't mean that the delays that a garbage collector incurs haven't been paid attention to. If you go back through the history of the Go language, you'll actually see the past few versions have had a huge emphasis on reducing the amount of time that the application has to pause during a garbage collection cycle. And at this point, they're actually really, really fast, almost to the point that you don't know that a garbage collection happened. In order to address that concern of concurrency, Go does have concurrency primitives built right into the language. And we'll talk about that as we go through some of these videos. But instead of having a library that we're going to have to import in order to work with concurrency, we're going to be able to do concurrent development right there in the base language. Finally, Go compiles down to a standalone library, which means when you compile your Go application, everything is going to be bundled into that single binary that's related to the Go application itself. So the Go runtime is going to be bundled in there. Any libraries that you're depending on, they're going to be compiled in there. So you don't have to worry about reaching out to external libraries and DLLs and things like that in order to make your application work. And what that gives you is version management at runtime becomes trivial, because you simply have one binary, you deploy that binary, you run it, and all of its dependencies are there. Now keep in mind, when I say dependencies, I mean the Go dependencies. If you're going to build a web application and that has HTML resources and CSS, those have to be bundled along with the binary, but the binary itself is standalone and self-contained. Okay, the next thing that I'd like to do is show you some of the resources that are available to you as you start to explore the Go language. One of the most useful resources that you're going to be able to take advantage of as you're ramping up on Go is Go's website here at golang.org. Now, why is it golang.org? Well, if you take a minute to think about a language called Go, that doesn't really lend itself to unique search results in Google or Bing. So golang.org it is. As a matter of fact, a lot of places that you see Go mentioned, you're going to see it actually described as Golang because that makes it a little bit more unique when you're looking for search results. So the first thing that you might notice as we go into the homepage here is this isn't really laid out like a lot of traditional homepages. This, in my opinion, is very much an engineering homepage. So instead of a lot of design aesthetic, this gets right into the engineering aspects and shows you how to start working with the language. So this yellow box over here is going to be your entry point for your first Go application. So if we go ahead and click this Run button, you see that we almost instantly get an application sent back to the server, it gets compiled, and it gets run for us. So we can start playing around with Go code without installing anything on our local machines. And we're actually going to take advantage of that through this first few videos. As a matter of fact, if I make a small change here, so maybe if I say hello YouTube peoples and run that again, then I'm saying hello to you all. So hi. So it's as simple as that in order to get started with the Go program. Beside that window, we see this Download Go button, and that's going to take you to resources that you're going to be able to use in order to download the latest Go binaries, as well as download older versions of the runtime. And if there's an unpublished version, for example, at the time I'm recording this, Go 1.8 is at RC2, you can go ahead and download that, install that, and check that for bugs and play around with new features in the language. If we come across to the top, we see this Documents link here, and this is going to be another critical resource as you're starting out with the language. As a matter of fact, you're going to refer back to this page quite often. But if you really want to walk through on the website a tour of the Go language, then I would recommend you go to this Getting Started link. This is going to get you started downloading and installing the Go compilers and tools and things like that. And you can see as we navigate there, it's going to show you the different architectures that you're going to be able to use with Go, and there's quite a few, and how to get started on each one of those. If we keep continuing down, the tour of Go is kind of an introduction to the Go language that takes you through a gradual introduction. So it's going to start out with some very simple applications and then build up more and more and more and help you understand what's going on with Go concurrency and things like that. Effective Go is a very useful article, especially as you start to mature in your understanding of the language and really understand how the Go language is used. So I would encourage you to go into that. It's a pretty lengthy read, but you should consider this required reading if you're actually going to start building non-trivial Go applications. But we're not going to worry about that right now. We got plenty of ways to go before we need to get through all of this stuff. And then down here at the bottom is some reference information. This is more advanced documentation that you're probably not going to need right away. But for example, the command documentation gives you a lot of information about the Go tool itself that you're going to use for local development with Go. There's a lot of things that the Go program does, and this is going to help you understand how to navigate that. The packages link is perhaps where I spend the most time on Go's website, and this gives you documentation for all of the libraries that are built into Go. So when you install Go and you install the Go binaries and tools, you're going to get all of these libraries available to you. So just scanning down, you can see that we've got different libraries that are targeted at working with archives. We've got some cryptography libraries, database drivers. Continuing to go down, we've got some things for working with HTML and network traffic. Now, some things that you might find missing here are we don't have any GUI libraries. That's because at this point, Go really isn't focused on the use case of client application development. So Go is really targeted at building servers and web applications, and so that's where a lot of the libraries are going to be focused on. There are some projects that are working on mobile applications using Go, as well as client-side applications using Go, but they're not officially supported at this point. If we come over to the project link, we're going to find some information about history of the project, what releases have come out and when, as well as some links to mailing lists and resources that you can take advantage of if you want to keep track of the development of Go as a language, as well as if you find an issue in the Go language, you can see some information here on how to report that issue. And then we've got the help link here, and this is going to be one of your more important links as you get started here, because this is going to be your on-ramp into the community. Now, the two most active in my experience are the Go forum, which is a nice discussion forum that allows you to post your questions and get people to answer back. But if you want something a little bit more real-time, then the Gopher Slack is a Slack channel specifically targeted at Go development. And there's multiple sub-channels in there for new developers, for library developers. Even a lot of the Go meetup groups have their own sub-channels on the Gopher Slack. So if you want to get on the Gopher Slack, then I would encourage you to come over here to another website called Golang Bridge. And this is what I consider the on-ramp to the Go community, because Golang Bridge is specifically there to advocate for the Go language and to make sure that the community is healthy and strong. As I said, one of the key aspects of the Go language is a focus on having an excellent community. And really, it's Golang Bridge and the awesome people that support it that are making that happen. So if you scroll down a little bit, you can see some links to the online communities. If you want to join the Slack channel, you do have to receive an invite. So this link here is going to take you to the form that's going to allow you to get that invitation. And there's no problem getting the invitation. The only thing that they ask you is to read the community guidelines. There is a code of conduct that just makes sure that everybody's going to be treated respectfully in the community, just to make sure that we're all here trying to help each other out. And the last thing that I want to show you on the website is this play link here. Now this link just flies out an editor, and this is really nice because this is available throughout the site. So if I come to the packages, and let's just say I dive into the network package, and I'm learning about some network function, then I can go ahead and pop into the play. I can create a real quick proof of concept Go application in order to make sure that I understand how that's working. And again, just like we saw on that homepage, if I click run, then I can go ahead and execute that. Now there are some limitations. Obviously this application is sent to the back end, and there are some limitations. You're not going to be able to read the file system of the back end, for example. But a lot of the things that you want to play around with, you can play around with in this online environment. Now, another place to get at this playground is over here at play.golang.org, and this is the last thing I want to show you in this introductory video. So this is going to be the environment that we're going to focus on, and actually let me make that a little bit bigger so maybe it's a little easier for you to see. But this is going to be the environment that we're going to focus on as we start to learn the Go language. So we're going to learn the basics of a Go application here. We're going to start playing around with how we're going to work with variables and logic and looping and things like that. Now, eventually we'll get to installing a local environment, and you can certainly take advantage of the other resources on Golang's website if you want to get there before I create a video on it. But I think that there's a lot that we can talk about without making a commitment to setting up a local development environment by just going through this playground here. So if we take a second look at this application, we see some of the key aspects of any Go program. Now the first thing that you see at the top is this statement package main. Every Go application is structured into packages. So every Go file that you're going to have is going to have to declare what package it's a part of. And main is a special package because main is going to be the entry point of any one of your applications. Down below that, we have an import statement, and this is the statement that we're going to use in order to import additional libraries. So this library is called FMT, which, yeah, you actually say that in the Go community. I can't bring myself to say that, so if I call that FMT, I hope that you'll forgive me. But in the Go community, you will often hear this called FMT, and this is the package that's going to allow us to format strings. So you see down below here in our main function, which is the entry point of our application. So the main function in the main package is always going to be our application entry point. And this is going to be where we're going to contain our first code that's going to run in Go. So we're going to call into the FMT library, and we're going to pull out its println function. And that println function takes one argument, and that argument in this case is a string. So we're going to print out hello playground. Now if I go ahead and run this, then down below at the bottom of the screen here, you see hello playground gets printed out, and then it says program exited. If we have an error in the application, say if I delete this quotation mark and run, then you're going to get a compiler error printed out at the bottom that's going to help you debug your application. So this online environment is going to be very good for you to get started because it's going to help you through understanding what's going on. So for example, we see here in line 8, it got an unexpected semicolon or new line when instead it was expecting a comma or a parenthesis. And the reason for that is because this closing parenthesis actually became part of the string, so the line terminated early, and it didn't have an end to the function call. So if we go ahead and re-add the quotation mark and run, we're good to go, and we've got our first start in a Go application. So I hope that this was helpful for you. A little bit of background in a language that you're going to be learning, I always find is a little bit valuable. It helps to understand the motivations for the creation of the language and the major features in order to understand what problems that language is going to try and solve and how it's going to go about trying to solve them. What I want to show you is how to get started setting up your own local development environment to program with Go. Now I know in the last video I showed you this website here, and I said that this is what I want to use, that is the website at play.golang.org, and I said that this is the website that I want to use in order to show you a lot of the concepts that you're going to need to be familiar with the Go language. And that's still my plan, but as I thought about it, I decided that it doesn't really make sense to force you to use the playground just because it's a really good place for me to demonstrate concepts. So I want you to have all the tools available to you to set up your own local Go development environment so you can play around with creating your own applications as you learn about this wonderful language. So the first thing that we're going to need to do is we're going to need to download and install the Go language and the Go tools itself. And so in order to get started with that, we're going to start over here at golang.org, and we're going to click on this download Go link here. Now this link is going to take you to all sorts of different versions of Go. But in general, if you're getting started, just pick the latest stable version that's available for you, and it's not going to steer you wrong. Now if you're a Windows user, then I would encourage you to click this MSI link. It's going to download an installer, and Go is going to be put on your system automatically. However, if you're using OS X or Linux, then I would recommend that you go to this installation instructions link here and follow the instructions here. Now you're still going to need to download the Go binaries, but if you scroll down just a little bit, you're going to see this command here, and this is going to give you the tar command that you're going to need to use in order to unpack the Go binary and install it onto your system. So I've already done that, and I can show you that by opening up a terminal here, and the default location to put Go is in the user directory underneath local, and then in a folder called Go. So if we look at there, and I look at the contents there, I see that I have all the Go tools installed. So with the Windows installer, all it's going to do is it's going to place these into /Go, and I would strongly encourage you, if you can accept these default locations, that you go ahead and do that, because it's going to make setting up your environment just a little bit simpler. Now after we get Go installed, we have a little bit of configuration in our environment in order to be able to use Go effectively. So I'm going to come back to my home directory here, and I'm going to make a change to my bash rc file. Now I'm on Ubuntu, so it's going to be in my bash rc file. If you're in OS X, it's going to be your bash profile. If you're in Windows, basically what we're doing is we're setting environment variables. So if I open that up and come down to the bottom, then I see that I've got the pre-generated bash script. I'm not going to really worry about that, but there's a couple of variables that we're going to need to set. Hello everybody, I need to pause the video here for a second and make an important announcement. So as soon as I originally released this video, Dave Cheney came in within a couple of minutes and he expressed a concern about one of the things that I'm about to talk about. Now I'm about to talk about setting a couple of environment variables here and showing you how they work. Now one of those variables is called GoRoot. And setting GoRoot has been shown to cause problems as you move through different versions of Go, especially if you've got multiple versions of the language on your system. So, if you want more information about that, Dave has a really good blog post here that you can go to learn more information about it. But for now, please keep in mind, if you're able to install Go at its default locations, which on Unix or Mac is going to be /user/local/go, and on Windows is going to be C:\\go. If you're able to do that, please do that and then go ahead and avoid setting GoRoot. Now you will need to set the path variable to GoRoot's bin directory in order to access the Go executable, and you will need to set GoPath, which we're going to talk about after that. But if you can avoid setting the GoRoot environment variable, it's going to save you a lot of heartache. So while I'm going to show you how to do that, in case you do need to set it, please avoid that if at all possible. Okay? At this point, I'm going to resume the video and continue talking about the environment setup. Now the first variable that you're going to need to know about is called GoRoot. Now if you've installed Go to its default location, you're not going to need to worry about this. But if you decided to install Go somewhere else, for example, maybe you've installed it in your home directory, then you can go ahead and set GoRoot, and that'll tell the environment where to go to find the Go binaries. Now the next thing that we want to do is we actually want to set a path variable to the Go binaries themselves. So I'm going to go ahead and export a path variable. And that'll of course start with my existing path, and then I'm going to add on to that GoRoot, and then I'm going to whack on the path /bin. So there's quite a few binaries that you're going to be using on a regular basis, and those are in GoRoot/bin. So you're going to want to make sure that that's part of your path. Now once I do that, let me go ahead and save this, and then I will use the source command in order to get my shell to reread the bashrc file. And then I should be able to test to make sure Go is available by typing Go and version. And you can see here I'm running Go version 1.8, release candidate 3. Okay, now there's one more thing that we need to do in order to get our environment fully set up. And I'm going to go back into my bashrc file in order to do that. And that is the setting of a second environment variable. So we have GoRoot, and that's going to tell the environment where Go is installed. But we're also going to be downloading a lot of packages as we work with Go, because we're going to be taking advantage of libraries that other people have published in order to build our own applications out. So those applications, as well as our own source code, are not going to be located with the Go binaries. They're going to be located in a path that we're going to specify with another variable called GoPath. Now GoPath is either one of the most awesome or one of the most horrible things about Go, because it gives you this really nice way to specify where your Go projects are located. However, it does kind of push you towards having this monolithic repository of all these binaries and your applications tied together. So I'll show you a little bit of a hint on how to work with that. But for now, let's go ahead and set a GoPath variable in my home directory, and then I will call this golib. Now just like with GoRoot, we might have some executable binaries that are going to be stored in our GoPath. So I'm going to go ahead and export on our path again, and we'll start with our existing path, and then I want to add on GoPath/bin. That way, if we install any libraries that have executables, and we will be installing libraries that have executables, then we're going to be able to track that. Now, just to show you real quick what that's going to do, let me go ahead and save this out, resource my bashrc file, and then I've actually already created this folder here called golib. Now, if I go into golib and I look at the contents of that, it's currently empty. But I can change that by using a tool called goget. So if I get a library that's at github.com/nsf/gocode. This is historically the library that people use to provide autocomplete functionality in their Go applications. So if I go ahead and hit enter, and wait a second, then go back into my golib folder and look, now I've got some contents here. So if I look in the bin directory, I've got this Go code executable, and if I come back to the source directory, then I see that I've got this github.com folder, and inside of that is NSF, and inside of that is Go code. So if I come in here, here's all of the source code for the Go code library. So when I'm working with Go code, it actually downloads the source code and compiles it into the Go code library for me, and that's what that GoPath is going to do for you. The problem that you might run into is that this use of GoPath tends to drive towards monolithic repositories. So you're going to have Go code, you're going to have your own code, you're going to have all sorts of other libraries, all put into this one location. Now, when I create my courses, that creates a lot of visual clutter, and so that isn't exactly the form of GoPath that I use. what I do is, coming back into my bashrc file, is I actually use a capability of GoPath to create a compound GoPath. So instead of a single path here, I'm actually going to re-export GoPath, and I'm going to add on an additional path to this. And I'm going to add home, mic, and code. Now, a lot of times when I'm teaching courses, I only need 2 GoPaths, and so I've got GoLib, and that's going to be where all my third-party libraries go. And then I'm going to have another folder that's going to be what's called my workspace location. So let's go ahead and write this out. We'll source this again. And now I've got the full GoPath. So if I come into my GoLib and I remove everything from it, now it's empty again. So if I go ahead and go get that repository again at github.com/nsf/gocode, and now you see that it actually goes into my GoLib folder. If I come into my code folder, which I also created earlier, that's still empty. So the first segment of your GoPath is going to be used by GoGet in order to store your files, but all of the segments of your GoPath are going to be searched for source code. So that's going to really help us as we're setting up our workspace. So speaking of which, that's the next thing that I want to do. So a workspace in Go isn't anything special. The only thing that you need in order to create a workspace is to have a single directory called src in it. So if I add a directory called src into my code folder, then I've got a Go workspace. Now src, as you might expect, is where you're going to keep your source code. So when I set GoPath to /home/mic/code, it's going to look for an src directory in order to find my source code. Now there are 2 other directories that you might find in a workspace that are interesting. Now we found one already when we installed that GoCode library, and that's bin. So anytime we're working with a project and a binary is created, it's going to be put into that bin directory. And that's also why we added that bin segment to our path. The last directory that you might find in your workspace is a PKG directory. So if we're compiling something and it's going to generate an intermediate binary, which means it's not going to be a fully compiled application, it's going to be an intermediate step. So for example, if we're taking a third-party library and we're integrating that into our application, then the PKG directory is where those intermediate binaries are going to be stored. And the reason those are created is so that they don't have to be recompiled every time. So when you compile your Go application, Go is going to check to see if any of the source files in that directory have changed since the last time it compiled them. If it hasn't, then it's not going to recompile that package. It's just going to go ahead and link them into the binary that it's creating for you. Okay, so let's go ahead and clear this out, because that's getting a little bit cluttered. And now let's set up an editor to work with GoCode. Now there's a lot of editors that are out there, and so what I'm going to show you is just one, but feel free to explore the options for your favorite editor, because there's probably a Go plugin for it, and all of these plugins are really good right now. So I'm going to show you the one that I've been using lately, which is Visual Studio Code. Now it might be a little bit surprising. Microsoft, oh my goodness, they're doing all this really awesome stuff for the open source community, but it's really true. One of the best development experiences that you're likely to come across with Go is in this Microsoft product running on Linux. So I've already installed it, but if you do need to install it, you can come here to code.visualstudio.com. It's going to give you the binaries. In this case, I'm running Ubuntu, so I would download this .deb file and install that onto my system. And then I'm going to be able to run that by simply typing code in my application launcher, or I've already set up a shortcut over here in my taskbar. So as soon as I run that, I'm going to be presented with this. Now you can see I've already opened up a folder here. You can open up a folder to your workspace by simply File Open, and then pick your folder that you want to be working with. So we're going to be working with code. But there is one setup step that I need to go through before Visual Studio Code is quite ready to go. And that is, I need to install the plugin that's going to allow it to work with GoCode. So if I click this button down here called Extensions, then I have a list of all sorts of extensions that I can add in for Visual Studio Code. Now right here is the Go extension by Luke Hoban. Now there's a couple of Go extensions, but I would strongly recommend you use this one here by Luke, because it is really amazing. It offers a lot of capability and really makes Visual Studio Code a first-class environment for developing Go. Okay, and as fast as that's been installed, and it was that fast because it's been cached from earlier, and then I'm all set and ready to build my first Go application. So let me go ahead into this source directory, and I'm going to create a folder that's going to contain my source code. Now your first temptation might be to just plug in your source code right here in your src folder, but I wouldn't recommend that. The standard structure that you're going to use in a Go application is to mirror where your application is going to be in source control, and that makes it Go gettable. So in this case, if I was going to keep this file in GitHub, I would create a folder called github.com, and then underneath that, my GitHub account is VANSIMKE. Don't ask, long story about why I called it that. And then I would have an application name. So I would call this maybe first app. And that's the folder that I'm going to store my application in. And the reason for that is if you think about if I check this into GitHub in a repository called first app, when I go get that, it's going to recreate this structure. And so you want to create your applications following that structure. So now I'm ready to create my first file, and I will call that main.go. And then I can start adding in my source code. So the first thing that I'm going to add is package main. And then when I save this, it looks like I expected something to happen here, and it's not happening. I think it's because, it told me that I needed to reload the environment. So I'm going to go ahead and do that. So I'm going to exit out of Visual Studio Code, and it should kick right back off, but it has to initialize the plugin. So now I see what I was expecting to see. And that is that the Go plugin has recognized that I don't have all the tools that it needs in order to provide me all the support that it can. Because the Go plugin for Visual Studio Code is actually like a lot of the plugins in other languages. It takes advantage of these language services. For example, it's talking to me about GoLint. GoLint isn't available on my system, and so it's not going to be able to provide linting capabilities. So basically, the Go plugin calls out to all these language services. The nice thing about that is if you decide to flip between different editors, your experience is pretty much the same because they're all relying on these same language services in order to provide you the capabilities that you have. So let me go ahead and install all. And you can see there's a pretty long list of libraries that it's installing for me. Okay, and now they're all installed. So that took about a minute to install all those dependencies. So I expect that you'd probably have a similar experience in your own environment. Now before we start adding anything else, I actually put some quotation marks around this package, so that's not going to be correct. And now I'm ready to start actually building out my program. So let me go ahead and put in an import statement here. And we haven't talked too much about imports, but we have mentioned a little bit about packages. Packages are how code is organized into sublibraries inside of Go. So for example, if I want to build a web application, then I might pull in the net HTTP package that you see here in order to set up my web request handlers. But for now, I just want to do a simple hello Go example, and so I'm just going to import the FMT package. But you notice that the Go plugin for Visual Studio Code gives me autocomplete. So any library that's available on my Go path is going to be found here. So now I'm going to create a simple function called main, and inside of that I'm going to access the FMT package, and notice that I get autocomplete functionality here. So I can go ahead and say I want to call the println function, and it gives me the signature for that function. So I can go ahead and add that in here, and then I just want to say hello Go. Okay. So in order to run this inside of Visual Studio Code, you do have the ability by pressing Control backtick. You can open up a terminal right here inside of the editor, and there's a couple of different options that I have in order to run my application. So the first thing that I can do is I can use Go's run command, as you see here, and I can give it the path all the way through to my source code. So if I come and I just keep tabbing through, then I'm going to get source/github.com/vansimke/firstapp/main.go. So if I run that, then it'll compile that temporarily and run that for me. And it'll also compile in any third-party libraries. So the FMT package was compiled in as well. Now that's a really good way to get a really quick run. Another way that you have available to you is to use Go build, and Go build takes the actual package path. So all we're going to do here is compile the first app package. Now, if it finds a main package with a main function, then it's going to compile that as an executable, like you see right here in my home directory, so I can go ahead and run that. Now, the last build tool that I have available is Go install. Go install is actually expecting to be pointed to a package that has an entry point, and it's going to install that into your bin folder. So let's go ahead and see that work. So we'll go to github.com. my username for GitHub, and then first app again. So notice I'm using the package address. I'm not using the folder path. If I run that, notice I don't get anything in my main directory, but if I come into this bin folder here, now I've got first app over here. So if I come back to my terminal, bin/first app, run that, I get hello Go printed out again. Okay, so the last thing that I want to show you, if I come back over to the terminal, so you see how we have all the packages that we're working with locally over here in this code directory. If I come to the first element of my Go path, which is golib, and look at that, you'll see that this has started to become a pretty busy place here, because now I've got 3 source folders, and if I come into github.com, you'll see that I've got quite a few packages. So now all of these third-party dependencies aren't cluttering up my main workspace. They're all in this golib folder, and then I can focus on my development in my code folder. Now the last place that you're going to see packages is over in the Go installation directory. So if I look in that folder, you see here that I have this directory called source. So the Go source code itself is in fact a valid Go workspace. So if I come in here, look at the folders in here, you see these are exactly the Go standard library. So here's FMT here. You see if I scroll down a little bit, the net package, if I go into the net package, you'll see that that contains the HTTP package. If I come into the HTTP package and list those contents, you see all of the source codes for all of the modules that you can see over here at golang.com. So if I follow that through over here, scroll down to net and HTTP, you see all of the capabilities that are available in here. Well, all of those are provided by this source code here. So if you have any questions about how any one of those libraries work or how something's configured, you can jump right into the source code and see how it's all put together. Over the last couple of videos, we've laid some foundation by talking about the history and the features of Go and working through setting up a local development environment. Well, today's the day that we're going to start a discussion about the Go language itself by discussing how to work with variables. So in order to fully cover how to work with variables, there's several topics that we're going to need to cover. We're going to start by learning how to declare variables. Then we'll move into a discussion about how Go considers redeclaration of variables and this concept of shadowing. After that, we'll talk about visibility, where we're going to learn how we can control what aspects of our program can see a variable that we create. Then we'll talk about naming conventions. And finally, we'll wrap up with a brief discussion about how to convert variables from one type to another. Okay, so let's go ahead and get started. So I'm going to be using the playground in order to host our conversation. That way you can follow along whether you've set up a local development environment or just want to follow along online. So as you can see, when we first load up the playground, we've got this one statement program, which is just printing out the string hello playground to the bottom of the screen when I click this run button here. Now this statement can only ever do one thing because we're passing in a string literal. And similarly, if I pass in the number, say 42, and run it, then we print 42 out. Now, no matter what we send to this println function, it's only going to ever do that one thing. So in order to provide a little bit more flexibility to our application, we're going to introduce variables. So there's actually 3 different ways to declare variables in Go, and we're going to go through each one of those, and then we'll talk a little bit about where you might use each format. So the first thing that we can do is actually declare the variable itself, and that'll be done using this kind of a statement. So we're going to start with the var keyword, then we're going to have the name of the variable and the type of the variable. Now if you come from another strongly typed language, this might look a little bit backwards, because you might be expecting to see something like int I. Well, that's not actually how Go works. And if you think about it, the way Go structures things actually looks more like how you read it. So I'm going to declare a variable called I that's going to be of type integer. So the way you declare variables in Go is pretty much the same way that you speak. And so it might look a little bit odd when you first start working with it, but it very quickly becomes intuitive. Now that we have our variable declared, we can go ahead and assign a value to it. And we'll do that simply with the equals operator. So once we have that set, we can go ahead and replace this with an I, run it, and we print the value 42 out. And since variables in Go can vary, we can go ahead and change the value of that to say 27. When we run again, we get the value 27 printed out. So now, even though the statement can only ever do one thing at a time, the program that runs up above this format statement can actually influence the value that's printed out to the console. Okay, so let's go ahead and get rid of this, and then explore another way to initialize this variable. Because one of the things that we're trying to do in Go is we want to keep things simple, so if we need multiple lines, then we'll go ahead and do that, but we don't want anything to be more verbose than we have to. So we can actually combine these 2 lines into one like this. So we can initialize the variable I as an integer and assign the value 42 in the same line. So if we go ahead and run this, then no big surprise, we get the value 42 printed out. Now this is actually still making us work a little bit harder than we need to, because since we're assigning the value 42 to this, the Go compiler can actually figure out what data type I needs to have. So we can go ahead and tell it to figure this out for us by replacing all this text with this text here. So if we just say I, and then use this :equal operator and the value 42, and run this, then we get this really nice, concise way of setting things up. Now, where are you going to need each one of these? Well, let me go ahead and add them back in so we can talk about them. So we'll set var I integer, I equals 42, and then we'll use var j integer equals 27, and then we'll set up k, and that's going to be equal to 99. So we have these three different formats. So when are you going to want to use each one of these? Well, the nice thing about this first format is there are going to be times when you want to declare a variable, but you're not ready to initialize it yet. So for example, if you want to declare a variable in the scope of this main function, and then you have a loop or something like that that sets up a local variable scope, and that's where the variable is actually going to be assigned, then you can go ahead and use this first syntax. The second syntax is valuable if Go doesn't have enough information to actually assign the type that you really want assigned to it. So to show that, let me go ahead and add another print statement here. And I'm going to need to comment these other lines out in order to make things happy for us. So let me go ahead and change this println to a printf. And what this is going to do is it's going to allow us to provide a formatting string and print things out that way. So I will print out the value, and then I'll print out the type of the variable. And then I'll pass in j twice. So if I run this, then we get the value 27, and no big surprise, it's an integer. But what if we want this to be, for example, a floating point number? Well, with this syntax, it's as simple as just changing this to float 32 when we run this. Then Go understands that we want to use 27 as a floating point number. Now, if we try that with k down here, so let me uncomment the k, switch this over to use k, and run, then you see that the number 99 is inferred to be of type integer. Now we can influence that a little bit by adding a decimal point, and that's going to give a hint to make that a float 64, but there's no way to use this colon equals syntax to initialize a float 32, for example. Go is either going to decide it's an integer type or it's a float 64 type. So if you need a little bit more control, then the second declaration syntax is going to be valuable for you. Now the next thing that I want to show you is how we can declare variables. Now we've been declaring variables one at a time and inside of a function. Well, another way that you can declare variables is up here at the package level. Now when you're doing it at the package level, you cannot use this colon equals syntax. You actually have to use the full declaration syntax. So we can declare variable I as an integer, set it equal to 42. So that works. Come down, wipe out this code, and then replace this with I. And you see that we have the value 42, and it's of type integer. So just like we have before, we can go ahead and tell it to declare that as a float 32. And the compiler recognizes, well, I can make 42 a floating point number. That's not going to be a problem at all. Now, of course, if you try something like this, the compiler has no idea how to convert the string foo to a floating point number, and so it's going to fail on you. Another thing that we can do at the package level is we can actually create a block of variables that are declared together. And to show you why that's valuable, let me just drop in some variables that we can play around with. Okay, so as you can see, I've got a little bit of Doctor Who on the brain here, and say I'm writing a program that's going to print out some information about the Doctor's companions. So here we've got a variable actor name that's going to be Elizabeth Sladen, then we got her companion name, which doctor she worked with, and what season she was on. So by declaring these variables like this, things are actually a little bit cluttered, because again, we want things in Go to be as clear and concise as possible. So all these var keywords are actually cluttering things up a little bit. So what we can do instead of this is actually wrap this whole section with a var block, and then we can actually get rid of the use of this var keyword. And now all of these variables are going to be declared because they're inside of this var block, and we can actually show that they're related somehow. Now they don't have to be related, that's a design decision, but we can do that. So if we had another set of variables that were related to a different context, so say for example we had a counter, and that was going to be an integer initialized to 0, then we can have multiple variable blocks at the package level. And that's just going to allow you to organize your application a little better and keep your code a little bit cleaner. Now the next thing that I want to show you, and let me just drop in some code here, is how variables work when you're trying to redeclare them. So as you can see in this application, we're declaring the variable I up here in the package scope, then I'm declaring it here inside of the main function, and then I'm redeclaring it here on line 11. Now if I try and run this, I'm actually going to get an error. And the error comes on line 11 here because there's no new variables here. So I can reassign the value of I, 13, but I can't declare a new variable here. And that's because the variable is already declared on line 10, and you can't declare the variable twice in the same scope. However, if I get rid of this line, notice that the application runs just fine and uses the value 42. So even though I is declared twice in my application, once at the package level and once inside of the main function, that's okay. And what happens is that the variable with the innermost scope actually takes precedence. So this is called shadowing. So the package level I is still available, but it's being hidden by the declaration in the main function. And I can actually show that by copying this line up here and running this. And now you see I get 27, which is the package level scope. Then I create the shadowing variable, set it equal to 42, and when I print out I again, then I get the new value of I. Now another interesting thing about variables in Go is that they always have to be used. So let me just drop in this example here, and let's walk through it. So I'm declaring a variable I, setting it equal to 42, then I'm instantiating a variable j, setting it equal to 13, but I'm only using I. So what happens when I run this? Well, if I do, I actually get yelled at, because j is declared and not used. And this is one of the things that's going to keep your Go applications nice and clean. If you have a local variable that's declared and not used, then that's actually a compile time error. And the reason that's really valuable is as your application grows and evolves and new features are added and old features are deprecated, you're very likely to end up with some old code hanging around inside of your functions. Well, if any of your old code are variables and those variables are no longer used, then the compiler is going to detect that for you so that you can make sure that you can clean those out. Now, another important thing to know about when you're working with variables is how to name them. And there's actually two sets of rules that you're going to need to keep track of. One is how naming controls visibility of a variable in Go, and the other is the naming conventions themselves. So notice that I've been creating lowercase variables. Well, that actually isn't always the case in Go, because if I'm declaring a variable, and let's just declare it at the package level, and I declare it as an integer with the name I, and I go ahead and work with that, then that lowercase variable name actually means that this variable is scoped to this package. Now this is a main package, and so this doesn't really matter so much, but when we get into working with packages, this becomes extremely important. So lowercase variables are scoped to the package, which means anything that consumes the package can't see it and can't work with it. But if I switch to an uppercase letter, then that's what's going to trigger the Go compiler to expose this variable to the outside world. So it's a very simple naming convention, and there's really only 3 levels of visibility for variables in Go. If you have it at the package level and it's lowercase, it's scoped to the package, so any file in the same package can access that variable. If it's uppercase at the package level, then it's exported from the package and it's globally visible. And the third scope is block scope. So when we have this main function here, it's actually establishing a block scope. So when we declare this variable I right here on line 10, that variable is scoped to the block. And so that's never visible outside of the block itself. Now beyond that, it's important to understand the naming conventions in Go. And there's a couple rules that we need to follow. The first is that the length of the variable name should reflect the life of the variable. So for example, in this example, we're declaring a variable I and we're using it right away. So having a very simple variable name is perfectly acceptable. And this is going to be especially true if you're declaring counters and for loops and things like that. It's very common to have single letter or very, very concise variable names because the lifespan of that variable is very small and the amount of time that you have to keep the meaning of that variable in your head is very small as well. However, if you're declaring a variable that's used for a very long time, then it's best practice to use a longer name. So for example, if this was going to represent the season number that our companion was on, so say season 11, and we use that throughout this entire main function, then we'd want to use a name something like season number. Now, if you're working with a package level variable, and that package level variable is going to be used in quite a few other places, then that's where you're going to want to use the most verbose variable name. Now, you still shouldn't get crazy. You shouldn't have 50 character long variable names if you can avoid it. So keep your names as short as you can, but make sure that the names of those exported or package level variables are clear enough so that somebody who's outside of that source file understands the meaning of it. The other thing I'd like to talk about is how to work with acronyms, because in other languages you might see variables like the URL, and then maybe this is http google.com. You might see variables named like this. Well, the best practice in Go is actually to keep these acronyms as all uppercase. So if you're working with a variable called the URL, then URL should be all uppercase. Similarly, HTTP and any variables like that. So anytime you see an acronym, make sure that that's all uppercase. And the reason is for readability. It's very clear. We're used to seeing URL and HTTP all put together. So when you read this variable, it's very clear that you're talking about an HTTP. Maybe you're talking about an HTTP request. That reads a little bit cleaner than if you go ahead and make those lowercase. So just some rules to keep in mind as you're creating variables. Now the next example that I want to show you is how we can actually convert from one variable type to another. So notice that I have two variables here. I've got the variable I on line 8 that I'm declaring as an integer with the value 42. And then I've got this variable j that's going to be a floating point number. Now what I want to do is I want to actually treat I as a floating point number and assign that value to j. So the way that I do that is using this conversion operator. So if you look on line 12, it looks like float is being used as a function, and in fact it is. And this is a conversion function. So when I run this program, you see that the first print statement on line 9 prints 42 as an integer. The second print statement still prints the same value, 42, but now it's been coerced into being a floating point number. Now you have to be a little careful with this, because if you go the other way, so for example, if we go from a float 32 to an integer, and then I convert that and run it, it looks like everything's okay. But keep in mind, a floating point number can have a decimal on it. So now I've actually lost information through the conversion. So the important thing about this is I have to explicitly convert, because if I just tried to do this, then I'm actually going to get a compile time error, because Go is not going to risk the possibility of losing information through that conversion. So you have to do an explicit conversion when you're changing types. That way it's your responsibility to understand if you're losing information or not. Now the other thing that's important to know is if I decide to work with strings, it's a very common use case to try and convert an integer into a string. Say for example you want to print it out to a log file. Well, if I run this, I get a pretty odd result. The first line prints out okay, 42, and that's an integer, that's okay. But then I get an asterisk that's of type string. What the heck happened there? Well, in order to understand that, you have to understand how strings work with Go. A string is just an alias for a stream of bytes. So what happens when we ask the application to convert the number 42 into a string is it looks for what Unicode character is set at the value 42, and that happens to be an asterisk. So if you want to convert back and forth between strings and numbers, then you're actually going to need to pull in the string conversion package, which you can find on Golang under packages. If you scroll down a little bit, you see string conversion here, and this is going to expose all sorts of functions that are going to make it a lot easier to convert back and forth between strings and other data types. So in this case, what we'd want to do is use the string conversion package's I to A function, which converts an integer, that's the I, to, that's the 2, and then to an ASCII string. So if we go ahead and run that, now you see that it properly converts the integer 42 into the string 42 and prints it out for us. So if you need to work with converting between numbers and strings, then go ahead and use that string conversion package. But if you're converting between numeric types, just keep in mind you can't implicitly do that conversion. You have to explicitly do it. And if you need to do that, then you can go ahead and use the type as a function. Okay, so we just covered quite a bit of ground. So let's go through a summary of what we've talked about throughout this video. Okay, there's quite a few things to keep in mind as we're working with variables, so let's go through and review what we talked about. The first thing that we talked about is the 3 different ways to declare variables. So we saw that we could declare a variable and then initialize it later. We saw that we can declare it and initialize it at the same time. And then we also saw that we can use this := syntax as a shorthand version of declaring and initializing a variable, and then we let the compiler decide what type to assign to that. Now normally you're going to use this third version. The only time you're really going to use the second version is when the compiler is going to guess wrong. And then the first version is sometimes useful if you need to declare the variable in a different scope than you're actually going to initialize it. We then talked about how we can't redeclare a variable, so within the same scope, we can't initialize that variable twice, but we can continue to reassign values to it, but we can shadow them. So if we declare a variable in a package scope, for example, we can redeclare that in a function scope, and that's going to shadow the variable at the higher level scope. All variables must be used in a Go application. So if you declare a local variable and that variable isn't used in the scope that it's declared or one of its inner scopes, then that's going to trigger a compiler error and you're going to have to go back and clean that up before your application is going to run. And again, the reason that that's really nice is as code evolves and it continues to be refactored and improved over time and features get retired, you don't have all these old variables hanging around and requiring allocations of memory when they're not being used for anything anymore. We also talked about the visibility rules. The first thing that you need to know is when you're working with package level variables, a lowercase first letter means that it's scoped to the package, which means all of the source files that are in the same package have access to that variable. If you have an uppercase first letter, then it's going to be exported globally, and so anything can work with that variable at that point. There is no private scope, so you can't scope a variable to the source code itself. However, you can scope a variable to a block by declaring it within the block instead of declaring it at the package level. We also talked about the naming conventions, and there are really two naming conventions that are used. Pascal case, which basically means you uppercase the first letter, and camel case. So when you're naming variables, you don't want to separate the words in the variables with underscores. You don't want to have them all in lowercase. You don't want to do anything like that. Just use standard Pascal or camel casing rules. The only exception to that is if you're working with acronyms, all of the letters in the acronym should be uppercase. The names of the variables should be as short as you reasonably can get them. So if you've got a very short lifespan of the variable, say for example a counter in a for loop, then having a one-letter variable name is perfectly acceptable. However, if you've got a variable that's got a longer lifespan, say for example it's used in a fairly long function, or if it's exported from the package, then having a longer, more descriptive variable name is certainly something that you should consider. However, please don't go crazy. Keep those names as brief and concise as possible. And the last thing we talked about are the type conversions, and how these work a little bit differently than other languages. In a lot of other languages, you would have to put the type in parens and then what you want to convert. In Go, it acts more like a function. If we want to convert an integer to a floating point 32 number, then we use float32 as a function and we pass the integer into it, and it's going to do the type conversion for us. We also learned that Go does not do implicit type conversion. So if you try and take a floating point number and assign it to an integer, Go's going to throw a compile time error for that, and that's because of the possibility of losing information through that conversion. So every time you're going to do a type conversion that might lose information, you're going to have to do that yourself so that you're making the decision, and then you can write whatever tests are required in order to make sure that information isn't lost. The final thing that we learned is when we're working with strings, then type conversions can start to get a little bit weird. So in order to handle the conversion between integers and strings and other data types and strings, we can use that string conversion package that offers a series of functions that make sure that the conversions happen the way that we expect them to. In today's video, what I want to do is introduce the primitive types that we have available in the Go language. Now, we're not going to be talking about every basic type that you can create. There are certainly collections and some more complicated types, and we'll introduce those a little bit later. Today, I want to focus on three categories of information that we can store in Go. We'll start by talking about the Boolean type, then we'll move on to the numeric types, and in that category we have integers, floating point numbers, and complex numbers, and then we'll move on to the text types. Okay, so a fairly simple agenda, but we've got a lot to cover. So let's go ahead and get started by talking about how we can work with Boolean data in Go. Boolean data is probably the simplest type of data that we can work with in Go, and it represents two states. You either have true or you have false. So in order to show you a simple example of working with Boolean variables, we can create a variable here and make it of type bool. So that's the data type that you're going to use when you're declaring a Boolean, and we can set it equal to a value. So for example, we can set it equal to true. And then we can go ahead and print out, using our fancy printf statement here, we can print out the value and type of this Boolean. And if we run that, we see that the Boolean true is in fact got the value true, and its data type is Boolean. So we can also initialize this to false and run that, and now we see false is also a Boolean. Now there's a couple of uses for Boolean variables in our applications. Perhaps one of the most common is to use them as state flags. So for example, say you're creating an application and you want to store whether a user is signed up for notifications when a report is generated. Well, you can use a Boolean variable in order to store true if they want that report or false if they don't. The other case, and perhaps the more common case for using Booleans in Go, is as a result of logical tests. Now we're not ready to talk about logical tests quite yet, but I can show you how Booleans are used in those tests. So if we create a simple variable here, and we use the equals operator to test if 1 equals 1, and then create another variable, and then I want to test if 1 equals 2. Now, the double equals operator is called the equals operator, and that's basically checking to see if the item on the left is equivalent to the item on the right. So 1 obviously equals the number 1, and 1 just as obviously doesn't equal the number 2. So if we print out the value of those using these two printf statements, then we see that a Boolean is actually generated as a result of this equivalency test. Now, when we get into talking about logical tests, we'll see that there are actually quite a few other logical tests that we can use, but this is a very common use case that we have. So we see, looks like I need to add a new line operator here. We see that the first operation does in fact generate the Boolean true, and the second operation generates the Boolean false. Now, the other thing that's important to know about the primitives is that every time you initialize a variable in Go, it actually has a 0 value. So we are assigning the value of n and m in this example here, but what happens if I just do this and print out the value of that? Well, in some languages, that would be uninitialized memory, and we would have no control over what printed out. Well, in Go, every time you initialize a variable, it has a 0 value, and the 0 value for Boolean is the value false. So you don't have to worry about initializing variables every time. If the 0 value is acceptable to you, you can certainly leave it like that. So Booleans are pretty simple. The next type that I want to get into are the numeric types. And these are a little bit more complicated. Because of all of the different types of numbers that we can work with in our applications, Go has a rich array of numeric types to choose from. Now, the first thing that we need to know about is the 0 value. And the 0 value for all numeric types is going to be 0, or the equivalent of 0 for that numeric type. So let's start talking about the integer types. So the first type of integers that we can work with are the signed integers. And those have several different data types. So we have the general int, which is an integer of unspecified size. And I say unspecified because every platform can choose to implement int as a different size. Now, the one thing that you're guaranteed is regardless of your environment, an int will be at least 32 bits, but it could be 64 or even 128 bits, depending on the system that you're running on. And this is going to be the default integer type. So if we do something like n equals 42, and then we print out the type of n, then you see that we get the value 42, and it's of type integer. Now, there are other types. So we can have 8-bit integers, which can range from negative 128 to 127. We can have 16-bit integers, which can go from negative 32,768 up to 32,767. Then 32-bit integers, which can go from approximately negative to positive 2 billion. And then if you need a really big number, you can go with 64-bit integers, and those go somewhere between plus and minus 9 quintillion. So if you need bigger numbers than that, then you've got a very large application that you're working with. And in that case, you're going to need to look into the big package from the math library, which can handle arbitrarily large numbers. So you can't get a number big enough for the big package to not be able to handle. Although, working with numbers that large, you're going to take a bit of a performance hit, and the numbers aren't going to be quite as easy to work with as using the primitive types that we're talking about here. Now, related to the signed integers are the unsigned integers. So we have the value 42 here, and just so you can see, we can create an unsigned integer, and I'll just pick a uint 16 and assign that the value of 42, and then let's go ahead and run that. And you see that now we have a uint 16. So there's an equivalent type of unsigned integer for every signed integer. We have uint 8, which is an unsigned 8-bit integer, which can go from 0 to 255. We have a 16-bit unsigned integer and a 32-bit unsigned integer. Now, what we don't have is we don't have a 64-bit unsigned integer, but we do have a type byte. And a byte is an alias for an 8-bit unsigned integer. And the reason we have that is because the unsigned 8-bit integer is very common, because that's what a lot of data streams are used to encode their data. Now, with these integer types, and again, unsigned and signed integers are basically the same type, we've got several different arithmetic operations that we can do. And these are built into the language. So if I just drop in this example here, you see that we've got an integer a set equal to 10, we've got another integer b set equal to 3, and we're doing the basic arithmetic operations that are available to us. So we can add, we can subtract, we can multiply, we can divide, and then this percent sign here is actually used for the remainder. So if I run this, you see that we get 10 plus 3 is 13, 10 minus 3 is 7, and so on. So we get the numbers that we expect. Now the one that you might not expect is this a divided by b. So 10 divided by 3 is 3 remainder 1, and so we get the result 3 out because when you divide an integer by an integer, you have to get an integer result. So the type cannot change during the operation. So when we do this, we're doing what's called integer division, and we drop the remainder. Now if the remainder is interesting, that's what this remainder operator is for, and then we can pick up that remainder 1 out of it. Now, just like when we're doing division, we can't change the type. So dividing an integer by an integer can't give us a floating point number, for example. We're also not allowed to add two integers of different types. So if we take this as an example, we've got the integer a set equal to 10 and an 8-bit integer set equal to 3. And if we try and add those together, we're actually going to get an error. So even though Go might be able to do that theoretically, it's very, very insistent that it's not going to work across types without your consent. So in order to make this work, we would actually have to do a type conversion on one of the variables to convert it into the type of the other. So just like we talked about in the last video, where Go is very, very hesitant about implicit data conversion, this is another example. Even though these integers are almost equivalent, Go is not going to make that assumption for you. You're going to have to do the type conversion. Now, a couple of other operations that we have are called the bit operators. So if I drop in this example, we see the 4-bit operators that we have. We've got the AND operator, we've got the OR operator, we've got the exclusive OR operator, and we've got the AND NOT operator. Now, what's going to happen when we run this? Well, let me just run this first and get these results. So you see that if we take A and B, then we get 2. If we take A or B, we get 11. And these might not make a lot of sense. So in order to clear things up a little bit, let me put in the binary representation of these, and then we can walk through what these are doing. So 10 is 1010 in binary, 3 is 0011. Now when we run into an AND operation, that's going to look for what bits are set in the first number and the second number. So as we can see, we've got 4 bits in each one of these numbers that are allocated. Actually, these are 32 or 64 bits long, but I'm ignoring all the zeros at the beginning of these numbers. So let's look at the 4 digits that matter. So if we look at these, then we see actually if we AND these together, we're going to get 0010. And in binary, that is 2. So 10 and 3 equals 2. Now if we do the OR means if one or the other is set. So we get 1 because A has the first bit set. Neither one has the second bit set. Both have the third bit set, so we're going to include that. And then B has the last bit set, so we'll have that. So now we end up with 1011, which is 1 plus 2 plus 8, which equals 11. Exclusive OR means either one has the bit set or the other does, but not both. So in that case, we're going to do 1001. The only difference between this and the OR operation is that third bit, where they're both set to true, and therefore we're not going to include that. Now in the AND NOT, that's kind of the opposite of OR, because with AND NOT, it's going to be set true only if neither one of the numbers have the bit set. So since the first bit is set in A, we're not going to include that. Neither one has the second bit set, so we're going to include that. Both have the third bit set, so we're not going to include that. And B has the fourth bit set, so we're not going to include that. So we get 0100, which is equivalent to the number 8. And that's how these bit operations work. The last example that I have to show you with integers is what's called bit shifting. So when we have this example here, the first print statement is going to bit shift A left 3 places, and the second is going to bit shift A right 3 places. So let's run this and see what that's going to do. And so we get the numbers 64 and 1. So in order to understand that, let me go ahead and put in these values so we can understand what's going on. So 8 is really 2 to the third power, and when we do bit shifting, we're basically adding to that exponent as long as we're dealing with the power of 2. Because really what we're going to do is we're going to take this 2 to the third and multiply it by 2 to the third, which is equivalent to 2 to the sixth. And 2 to the 6th is 2, 4, 8, 16, 32, 64. So that's how we get the 64. Now, when we bit shift to the right, we're going to take our original number and we're going to divide it by 2 to however far we're shifting. So we're going to divide it by 2 to the third. And in that case, we're going to get 2 raised to the 0 power, and any number greater than 0 raised to the 0 power is 1. And so that's how those operations work. The next data type that I want to talk about are the floating point types. So we have a lot of different integer types, so we can store a lot of different size numbers, but with integer types we can only store integers. So they can be positive or negative integers or 0, but we can't store decimal numbers. So in order to store decimal numbers in Go, we're going to use the floating point numbers. Now the floating point numbers in Go follow IEEE 754 standard, and in that standard, we're going to pull out 2 of the types. So we've got 32-bit floating point numbers and 64-bit floating point numbers. So if you're working with a 32-bit floating point number, you can store numbers between plus or minus 1.18 times 10 to the negative 38th, all the way up to 3.4 times 10 to the 38th. So from very small numbers to very large numbers. If you need even more precision than that, then you can use a float 64, and that can go from plus or minus 2.23 times 10 to the negative 308th, all the way through 1.8 times 10 to the 308th. So how do we create floating point numbers? Well, here's some examples of how we can do that. So line 8 here shows you how you're going to define your floating point literals almost all the time. So we're going to declare a variable n, set it equal to 3.14, and away we go. This next line here shows that we can use exponential notation. So we can use 13.7 times 10 to the 72nd, and that's going to be able to use the short form e72nd to stand for that 10 to the 72nd. So if I run this, we're actually going to get the final result here of 2.1 times 10 to the 14th as a floating point 64, but notice we didn't get any errors. So all three of those declaration syntaxes are okay. So that's how we can work with floating point numbers, and to show you how you can explicitly declare these, we can use, let me just do var n float 32, for example, and initialize that, and that's how you're going to declare a floating point number. Now, unfortunately, this number is a little big because we can only go times 10 to the 38th power. So if I comment that line out, things are going to run properly. If I come back in and make this a floating point 64, then we can restore this number. And that's another thing that's important. If you're going to use the initializer syntax on a decimal, it's always going to be initialized to a float 64. So keep in mind, you can't do arithmetic operations between float 64s and float 32s. So if you're just using the initializer syntax, you're going to want to make sure that everything's working as float 64. And if you forget, don't worry about it. The compiler will complain at you, and you can quickly go in there and make sure that everything's working properly. Okay, now speaking of arithmetic operations, let me jump in a couple of those, and you can see the arithmetic operations that are available with floating point numbers. So if I run this, we get the expected answers of adding, subtracting, multiplying, dividing two numbers together. Now, a couple things to notice here. When we divided a by b, we did in fact get a decimal result, because as long as we're working with floating point numbers on both sides, we can get a floating point result. As a matter of fact, we have to get a floating point result. The other thing to notice is we don't have the remainder operator available. That is only available on the integer types. Further, we don't have the bitwise operators or the bit shifting operators. So if you need to work with those, you're going to have to work with the integer types. The last type of numeric primitive that we have available in Go is the complex type. And this is really kind of exciting because this is fairly rare in the languages that I've worked with, where complex numbers are actually treated as a first-class citizen, and it opens up Go to be used as a very powerful language for data science. So if we come in and paste an example, you can see a very basic declaration of a complex number. Now there are two types of complex numbers. There's complex 64 and complex 128. And the reason we have that is we're basically taking a float 64 plus a float 64 or a float 32 plus a float 32 for the real and imaginary parts. Now here I've got a very simple complex number that's 1 plus 2i. If I go ahead and run that, you see that in fact it prints out as 1 plus 2i, and that's complex 64. So Go's parser understands the I literal as an imaginary number, and it uses that when you're creating your variable. Now we can actually go even simpler than that because I is considered special, and we can run this with just 2i, and we get 0 plus 2i down here in the result. Now what operations do we have available? Well, we can do addition, subtraction, multiplication, and division again. So I've got two complex numbers defined here. If I run this, then I get the expected result where the real parts are added together and the imaginary parts are added together, or subtracted, multiplied, divide, whatever operation we're applying. Now what happens if you need to decompose this down? So if I come back to our first example here, where we have 1 plus 2i, not every operation that I'm going to do with these numbers is going to need this to work as a complex number. So what happens if I need to get at the real part or the imaginary part? In order to do that, we actually have two built-in functions in the language. So let me wrap this n here with a call to the real function, and then I can follow that up with its partner, which is the imag function. Now what those are going to do is those are going to look at the complex number that you provide, and they're going to pull out the real part or the imaginary part. And these functions work with complex 64s and complex 128s. So if you run this on a complex 64, then the real and the imag function are going to give you float 32s out. If you run this on complex 128, it's going to give you float 64s out, because those are the data types used for the components. So if we run this, we see that we get float 32s out. If we convert this to a 128 and run this again, then we're going to get float 64s out, and it's going to break apart that complex number into the real and imaginary parts, so we can work with those however we need to. Now the complement to these two functions is the complex function. So if you're working along in your program and all of a sudden you need to make a complex number, how do you do that? Because you can't use this literal syntax. So in order to do that, we do have another function, and that's the complex function. And this takes two numbers. The first number is the real part, and the second number is the imaginary part. So let me go ahead and wipe out this line, get rid of these real calls here, and then run. And now that we see that we can take two floating point numbers, in this case they're considered to be floating point 64s because we're making a complex 128, and it creates 5 plus 12i for us. The last data type that I want to talk about is the text type. And text in Go falls into two basic categories. One I can talk a lot about, the other we're just going to touch on. So the first text type that we have available is a string. And a string in Go stands for any UTF-8 character. So that makes it very powerful, but that means that strings cannot encode every type of character that's available. For that, we need the other text type, which we'll talk about in a second. But let's just start by introducing a basic example here. So here I've got a string literal. This is a string. I'm going to print out its value and its type. So if I go ahead and run this, you see that this is a string prints out, and it's of type string. No big surprise here. Now, one of the interesting aspects of a string is I can actually treat it sort of like an array. Now, we haven't talked about arrays yet, but I can actually treat this string of text as a collection of letters. So if I do something like this, I'm actually going to ask it for the third letter because arrays in Go are zero-based. So I'm going to look for the 0, 1, 2. That's the third letter in the string, which is the letter I. So if I run this, I get an interesting result. I get the value 105, and that's a uint 8. So what the heck happened there? Well, what's happening is that strings in Go are actually aliases for bytes. So we can go ahead and convert this guy back, since a byte is just an alias for a string, and we can get our letter I back. Now, strings are generally immutable. So while I can inspect the second character, I can't do something like this. If I tried to run this program, let me just print out the full string here and run this, then I get an error. And there's actually quite a few things wrong with this. The first thing is I can't assign a string to a byte because I'd have to do a conversion. The second thing is I can't manipulate the value of the string. Now with the numeric types, I showed you that there were quite a few operations that we could perform with it. There is one arithmetic or pseudo-arithmetic operation that we can do with strings, and that is string concatenation, or in simpler terms, we can add strings together. So in this example, I've got the string s and the string s2, and as you can see down in the printf statement, I'm adding s and s2 together, and then we're going to print out their value and the type. So if I run this, you see that it just munges all the strings together, and it gives us the result. Now another thing that I can do with strings is I can actually convert them to collections of bytes, which in Go is called a slice of bytes. So in this example, I'm starting with a string, this is a string, and then I'm going to do a conversion to this collection of bytes, and I'm going to pass the string into that. So if we run that, we actually get this is a string, comes out as the ASCII values or the UTF values for each character in that string, and then you see that the result is a collection of uint8s, which is a type alias for bytes. Now why would you use this? Well, that's a very good question. A lot of the functions that we're going to use in Go actually work with byte slices, and that makes them much more generic and much more flexible than if we worked with hard-coded strings. So for example, if you want to send as a response to a web service call, if you want to send a string back, you can easily convert it to a collection of bytes. But if you want to send a file back, well, a file on your hard disk is just a collection of bytes too. So you can work with those transparently and not have to worry about line endings and things like that. So while in your Go programs, you're going to work with strings a lot as strings, when you're going to start sending them around to other applications or to other services, you're very often going to take advantage of this ability to just convert it to a byte slice. Okay, the last primitive data type that we have to work with is called a rune. Now, a rune is a little bit different than a string type in Go, because where a string type represents any UTF-8 character, a rune represents any UTF-32 character. Now, UTF-32 is a little bit of a weird animal, because while any character in UTF-32 can be up to 32 bits long, it doesn't have to be 32 bits long. For example, any UTF-8 character, which is 8 bits long, is a valid UTF-32 character. So there's all sorts of tricks that they have to do in the encoding of the characters in order to know whether the character is 1, 2, or 4 bytes long. So that makes things a little bit tricky to work with in Go. Now we're not going to get too deep into this subject, we're just going to talk a little bit about what runes are, and then I'm going to point you to some things that you can refer to if you actually need to work with runes in your application. So if we look at this example here, we're declaring the rune A. Now notice the difference here. If we were declaring a string, we would have double quotes. When we're declaring a single rune, we use single quotes. But if I run this, I'm going to get an interesting result. Notice I get the value 97, and it's an int32. Now that might seem a little weird. And the reason for this is because runes are just a type alias for int32s. So where strings can be converted back and forth between collections of bytes, runes are a true type alias. So when you talk about a rune in Go, it is the same thing as talking about an integer 32. Now you might think, well, that's just because we're doing some implicit initialization here. We're using that colon equals syntax. So let's specifically and explicitly declare this as a rune and try this again. And we get the same result. And again, that's because a rune is an integer 32. Now, you might be feeling a little lost here. So if I've got a UTF-32 character set, how do I work with that? Well, the answer comes from the Go APIs. So if I jump out to golang.org, come into the packages, and let me just jump to the strings package, and then I'll show you this. Notice this function here, read rune. So if you're working with a data stream that's encoded in UTF-32, then you have special functions that you're going to be able to take advantage of that's going to return those values out. So if we do read byte, which is going to read a single character, then we're going to get a byte out and a potential error. But with read rune, Go is going to look at the byte stream, it's going to pull off the next rune that's available, tell you the size of that rune, and then a potential error. So you're going to have all the information you need in order to re-encode that integer 32 that you're going to have back into its UTF-32 character. So things are a little bit more tricky when you're working with runes, and you're going to have to read into the APIs for the Go package that you're working with in order to understand how to work with them in your application. Okay, so that covers the primitive data types that you have to work with in Go. Let's go into a summary and review what we've talked about in this video. We covered a lot of ground in this video, and I understand that it might take a little bit of time to process this and really understand all the different options that you have for primitive data types in Go. Now, before we get into the summary, I do want to let you know that a lot of times the default data types that you're given are going to be perfectly fine. So if you're working with Booleans, you're going to get a Boolean type. If you're working with integers, you're going to get that signed integer type. Floating point is going to give you floating point 64, and so on. So you don't have to memorize every single data type. If you need a specific data type, then you can certainly refer to the Go documentation in order to find out what's available for you. So let's go through and review what we talked about. The first thing that we talked about was the Boolean type of data. We found out that it can take two values, true or false, and it's not an alias for other types. So in some languages, a Boolean is actually an alias for an integer, so you might use like -1 for true and 0 for false. Well, in Go, Boolean is its own type, so you can't convert back and forth between integers and things like that. You're going to have to work with Booleans as their own type. We also talked about the 0 value for a Boolean is the value false, and so if you initialize a Boolean and don't set a value for it, it's going to receive the value false. Then we talked about the numeric types. And the first type that we talked about were the integer types, and that broke down into two different types. We have the signed integers, and there are two classes, I guess you could say, within the signed integer type. There's the int type, which has varying size, but a minimum of 32 bits, and this is going to be the most common type of integer you're going to deal with in your applications. But if you need a little bit more granularity or a little bit more resolution or control over how much memory is assigned to the integer, then you can go all the way from int8, which is an 8-bit integer, all the way up to a 64-bit integer. We also have the unsigned integers, so where the signed integers have a plus or minus, and so they can't store numbers quite so large because they have to store a plus or minus bit. The unsigned integers can store larger numbers, but they can only ever be positive. And we have all the way through an 8-bit, which we can use the byte or the uint8 type for, all the way through 32-bit unsigned integers with the uint32. We have various arithmetic operations that we can perform on both integer types, so we can do addition, subtraction, multiplication, division, and that remainder operation. So remember, division with integers is going to give you an integer result, so you're going to lose that remainder portion. So if you need that, you can use that remainder operator to get it. We also have the bitwise operators, so we can do and, or, exclusive or, and the and not operations. And the 0 value for any integer type is going to be the literal value 0. So when you initialize an integer type and don't assign a value to it, that's going to be equivalent to the value 0. You're not just going to get whatever was in memory when that variable was initialized. And you cannot mix types in the same family. Now this is going to be true throughout all of the numeric types. If you have a uint16, for example, and a uint32, you cannot add those together. You're going to get a compile time error. The next numeric type that we talked about were the floating point numbers. So they follow the IEEE 754 standard. The 0 value is similar to the integer types, the value 0. And we have two different versions. We got 32-bit versions and 64-bit versions that we can work with. And we have several different literal styles that we can use to initialize them. So we can use a pure decimal like 3.14. We can use exponential notation, For example, 13E18 or 2E10, and it doesn't matter if that E is upper or lowercase, or you can do mixed. So for example, 13.7E12 is a perfectly acceptable way to initialize that. We do have addition, subtraction, multiplication, and division that we can do with floating point numbers. Now, we don't have the remainder operation, but the division operation is going to give us a true floating point result, so we're not going to lose our decimal portion. The final numeric type that we talked about were the complex numbers. The zero value of a complex number is 0 plus 0i, and they come in 64 and 128-bit versions. And the reason for that is the two components, the real and the imaginary component, are either going to be floating point 32s or floating point 64. So when you add those together, that's where you get the 64 and 128-bit versions. We have some built-in functions that we can work with. So we can use the complex function in order to create a complex number. We can use the real function in order to get the real component, and we can use the imag function in order to get the imaginary component of a complex number. Now what the data type that comes out of that depends on the size of the complex number going in. So complex 64 is going to give you a float 32 out from the real and the imag function, and a complex 128 is going to give you a float 64 out of the real and the imag function. We have the same arithmetic operations as we do for floating point numbers. We can do addition, subtraction, multiplication, and division. The final category of primitive data that we talked about were the text types. And in Go, there are really two different text types. The most common one that you're probably going to deal with are strings. Now, strings are represented as a collection of UTF-8 characters. They're immutable. You cannot change the value of a string after it's been initialized. You can concatenate strings together with the plus operator, and then you can convert them back and forth between a collection of bytes with this square bracket byte syntax and passing in the string. That'll convert it to a collection of bytes, and you can convert a collection of bytes back to a string by using the string conversion. The other type we talked about is a rune, and a rune represents any UTF-32 character. Now, runes are a little bit more complicated to work with because of the multi-step process that it takes in order to encode a character into the UTF-32 character set. So when we're working with runes as a primitive type, really all we're working with is an alias for an integer 32. Today I want to talk about constants and how you can use them in your Go applications. Now there are several things that we need to talk about with constants, so like we've been doing, I want to break this down into several categories. The first thing that I want to talk about is how we're going to name constants in our Go applications. Then we'll talk about typed constants, followed by a discussion about untyped constants, and we'll talk about the differences between those two and the options that each one gives us. And then we'll talk about a method of generating constants that are called enumerated constants. And finally, we'll end our discussion by talking about enumeration expressions, which are going to build upon the concepts that we're going to talk about in that first enumeration discussion. The first thing that I want to talk about is how we're going to name our constants. So all constants are going to be preceded with the const keyword that's going to let the compiler know that that's what we're trying to work with. Now, if you've come from other languages, you might be expecting that we're going to name our constants something like this, where we're going to have all uppercase letters and separate the words with underscores. The problem with that is if we do that in Go, then the first letter is going to be uppercase. And as you remember from our discussion on variables, if we've got an uppercase first letter, that's going to mean that the constant is going to be exported. And we don't always want that. So instead of this, we're actually going to name our constants the same way that we name variables. So if we had a variable that we wanted to call myConst, and we didn't want to export it, then we would start with a lowercase first letter, or in other words, we would use camel casing. And if we did want to export this symbol, then we would simply change that first character to uppercase. Now, assuming that we're going to be working with an internal constant, then we're going to switch this back to a lowercase first letter. And then let's talk about how we can create what's called a typed constant. Now, a typed constant is created very similarly to a typed variable. So we can start with the const keyword, then the name of our constant, and then we're going to list the type of the constant, and then we can set it equal to a value. Then if we want to prove that that worked out the way we expected it to, then we can go ahead and print out the value and the type of the constant, and we will do that by using this printf statement here. And then when we run this, we see that the constant is in fact created. It's got the value 42 that we assigned, and it's got the type that we assigned to it. Now, the reason it's a constant and not a variable is it has to remain constant. So if we tried to do something like this, change this to the value 27, then the compiler throws an error because we're not allowed to change the value of a constant. Another characteristic of a constant is that it has to be assignable at compile time. So for example, if I wanted to have a constant that represented the sign of pi over 2, then I might be tempted to do something like this. I'll create a float 64 constant, and I'll set it equal to the result of the sign function from the math library, and I'll pass in 1.57, which is approximately pi over 2, and then I can run this, right? Well, the problem with that is in order to determine the sign of that value, that actually requires the function to execute, which is not allowable at compile time. And so you can't set your constants equal to something that has to be determined at runtime. And that includes things like setting it equal to flags that you pass into your application when you run. If you're going to do that, you can't use a constant to store that value. Now, constants can be made up of any of the primitive types that we talked about in the last video. So if we have this example here, we've got an integer constant, we've got a string constant, a floating point constant, and a Boolean constant. And if we run this, we see that all of those print out exactly the way that we expect. We've got the integer, the string, the floating point value, and the Boolean value. Now, in an upcoming video, we're going to talk about the collection types. And the collection types are inherently mutable. So for example, you couldn't create an array and declare that to be a constant type. Arrays are always going to be variable types. Now, another characteristic that constants have in common with variables is they can be shadowed. So if we create a constant at the package level, and let's just make this an integer 16 and set it equal to the value 27, then we'll delete these guys and also these guys. Now we've got a constant called a declared at the package level that's an integer 16, and then we got a constant in the main function that's also called a, and it's an integer type. So if we update this printf statement to print the type of the variable, we see that looks like I need to print my variable twice. We see that the inner declaration of the constant wins. So not only can we change the value of the constant, but we can also change the type because the inner constant shadows that outer constant. And we can prove that by commenting this line out, running again, and we see that the package level constant wins. So you want to be a little careful here because if you're going to reuse constants, it's going to feel like those values are changing. So I wouldn't recommend that you take advantage of this, but if you do get into a situation where constants aren't evaluating the way that you expect them to, this is one possible reason. Now, when we're working with constants, they work very similar to variables when we're using them in operations. So if we bring this line back and set it equal to 42, and then what I want to do is declare a variable. So we'll declare a variable b as an integer and set that equal to the value 27. And then we can do a plus b. And let's see what happens when we do that. So if we run that, we in fact get the ability to add a constant to a variable, and the result is going to be a variable. And so since the constant and the variable are of the same type, we can perform the addition operation on there. Now, if our constant is of a different type, for example, if we made variable b an int16 and run this, then we get exactly the same failure that we get when we try and add two variables of different types together. Now, so far, all that we've been talking about are these typed constants, where after the constant name, we list the type. But we don't have to do that. We can use the compiler's ability to infer the type for us. So let's just go ahead and do that with this example here. When we run this, we see that the constant a is inferred to be an integer with the value 42. Now, given that the compiler's inferring the value, what do you think is going to happen if we do something like this? If we restore that previous example, where we're going to add this constant to an integer 16. Well, in fact, in this case, the operation succeeds, which might be a little bit confusing. But the reason that works is because what the compiler's actually doing when it sees this constant is it's basically replacing every instance. So the way the compiler sees this program is it sees it like this. So since we're taking a literal 42 and adding an int16 to it, that 42 is interpreted as being an integer 16. So the compiler doesn't say, oh, constant a equals 42, that's an integer and always an integer. Instead, the compiler is going to look for every time that we use the symbol a, and it's going to replace that with the value of the constant. And so we can do these implicit conversions when we're working with constants, which is something that we can't really do when we're working with variables. The next thing that I want to talk about are what are called enumerated constants. So let me go ahead and start that conversation out by wiping out what we have here, clean up our code just a little bit. And then I'm going to do this at the package level because this is where I've seen these most commonly applied. You could do these in a function level if that made sense in your application. So I'm going to declare a constant a, and I'm going to have that as an untyped constant, and I'm going to set it equal to this special symbol called iota. So when I run this, you see that a is evaluated to have the value 0, and it's inferred to have the type integer. So what is iota? Well, iota is a counter that we can use when we're creating what are called enumerated constants. So in this example, having an enumerated constant isn't terribly valuable. But one of the things that I can do with constants is I can actually work with them in a constant block like this. So when I'm doing this, I can create another constant, set that equal to iota, and another constant, and set that equal to iota. Now let's go ahead and clean up this because we already know what the type is going to be, so we don't need to be printing that out. And then let's print this command out 2 more times, switching to B and C. So now we're using iota 3 times, and when we get the result, we actually see iota is changing its value as the constants are being evaluated. So the first constant that's assigned has the value of 0, then 1, and then 2. Now another special feature that we can take advantage of with iota is that if we don't assign the value of a constant after the first one, then the compiler is going to try and infer the pattern of assignments. So in this example, we would expect to have an error because B and C don't have a value assigned. But since we've established a pattern for how to name the constants in this block, when we run, we actually get the same result. And that's because the compiler is going to apply the same formula. So it's going to apply B equals iota and C equals iota for us. Now, that value of iota is scoped to that constant block. So if we create another constant block, and in this case, we create a constant called A2, and set that equal to iota, copy this line, bring it down, and print out the value of A2. Then what we're going to find is iota resets to 0. So iota is scoped to a constant block. And what that lets you do is you can actually create related constants together, ensure that they have different values, and then if you have another set of related constants, you can start another constant block and ensure that they have unique values, but allow duplication between the values in one constant block and another. So what's an example of where you might use this? Well, let me just drop in this simple application. And what we're doing here is we're setting up a constant block where maybe we're trying to store the specialty of veterinarians in a veterinarian clinic. So a veterinarian could be a cat specialist or a dog specialist, or maybe we can take a snake specialist too. Now, as you can see inside the const block, I'm setting the cat specialist equal to iota. And then in the main block, I'm creating a variable and setting its value equal to cat specialist. So if I check to see if the specialist type is a cat specialist, then I in fact get the value true. Now that works just fine. And this also works if I, for example, use a dog specialist, assign that specialist type to be a dog specialist, run that, then that's going to work out just fine. So everything looks really good here, right? And this is a very common use for enumerated constants. However, one thing that I would warn you about is what happens if I declare this variable and don't initialize it to a type. Well, if I check to see if it's a dog specialist, I get false, which makes sense. But remember, what is the initial value of iota? Well, the initial value of iota equals the 0 value for an integer. And so in fact, even though we haven't specified a specialist type, it does show up as the value cat specialist. So what do we do about this? So there's a couple of approaches that we can take here. The first is to use the 0 value of the constant as an error value. So we can set this equal to error, then we don't need this statement anymore. And now, when we check to see if the specialist type is a cat specialist, we get the value false because cat specialist is equivalent to the integer value 1, which is no longer the 0 value of the integer. This is a very valuable approach if you want to check to see if a value hasn't been assigned to a constant yet. So you can specify an error specialist, and then you can check to see if that value is set equal to the 0 value of that constant. And if it is, you can handle that error because presumably you expect that to be initialized in some way. Now, if your application guards against that, and there's no reasonable way for this to happen, then you can take advantage of this underscore symbol, which is goes one and only write-only variable. Now, what's the value of a write-only variable? Well, with iota, we have to have a 0 value. We always have to start with 0. But if we don't care about 0, then we don't have any reason to assign the memory to it. So we can use this underscore symbol, and we'll see this in quite a few places in our Go applications. And basically what that tells the compiler is, yes, I know you're going to generate a value here, but I don't care what it is. Go ahead and throw that away. So if we run our application again, everything works just fine. But in this case, we can't actually get at the 0 value of this constant block. Now, the ability to create lists of enumerated constants with iota is very valuable, but things don't actually stop there. And the reason is, remember, the value of a constant has to be able to be determined at compile time. But there are some operations that Go is going to allow us to do. For example, we can do addition. So if we do this and run, then we get false again. But what happens if we print out the value of cat specialist? If we do that, and we're going to have to remove this line, then in fact, that expression got evaluated. So the first line, line 8, is evaluated to iota plus 5, which is 0 plus 5. The next line, cat specialist, iota increments, and the formula repeats. So cat specialist is equal to the value 6, dog specialist is 7, and snake specialist is 8. So this can be valuable if you need some kind of a fixed offset. Now a common use case for this is to use the bit shifting operators, because anything that we can apply to our primitive type, we can apply here as long as it's not a function expression. So we can do addition, subtraction, multiplication, and division. We can do remainder operations. We can do the bitwise operations. And we can do bit shifting, which is one of the more interesting use cases that we can take advantage of. And the reason is because we don't have the ability to raise to powers, because raising to powers in Go is a function in the math package. So we can't do that in our constant evaluations. But by bit shifting, we can raise things to the power of 2, because every time you shift a number one level, you're actually multiplying it by 2. So we have this example here, and I actually stole this from the Effective Go article on golang.org. So what we have here is we have an example of a constant block that's giving you constants that are equivalent to kilobyte, megabyte, gigabyte, terabyte, petabyte, and so on. So down here in our main program, what I've done is initialize the file size to some arbitrary value, and then I've got this printf statement, and this is basically going to format our result to print 2 decimal places, and then the literal string GB afterward. So this string here is basically saying I'm expecting to format a floating point number, and I'm going to give it 2 decimal places. This GB is a literal GB that's going to be printed in the result, and then we've got the value that's going to be used to fill this in, and that's going to be file size divided by the GB constant. Now you notice this constant block is set equal to 1, and then we're going to bit shift that value 10 times iota. So the first time we're going to bit shift 10 times 1, so we're basically going to multiply this by 2 to the 10th, and then we're going to multiply by 2 to the 100th for the megabyte, and then 2 to the 1000th for gigabyte, and so on. So when we run this, we get a really convenient way to format an arbitrary file size into a human readable format. And in the Effective Go article, it actually shows you how to put a switch block, which we haven't talked about, so you can make a decision about which constant you're going to use based on the size of the incoming value. So here we get this nice way to format this relatively difficult number to read to be the very easily read 3.73 gigabytes. Now another thing that can be very valuable to do is using bit shifting in order to set Boolean flags inside of a single byte. So if I paste this example in, we can see an example of that. So let's just say that we've got an application, and that application has users, and those users have certain roles. So inside of this constant block here, I'm defining various roles that we can have. So for example, you might be an admin, you might be at the headquarters or out in the field somewhere, you might be able to see the financials or see the monetary values, and then there may be some regional roles. So can you see properties in Africa? Can you see properties in Asia, Europe, North America, or South America? So in order to define these constants, what I'm doing is I'm setting the value to 1 bit shifted by iota. So the first constant is admin, is 1 bit shifted 0 places, so it's a literal 1. The second one is 1 bit shifted 1 place, so that's 2, and then 4, and then 8, and then 16, and so on. So what I have is each one of these constants is going to occupy 1 location in a byte. So down here in the main program, I'm defining the roles in a single byte, and I'm ORing together is admin, can see financials, and can see Europe. Now if you remember, ORing is going to be set to true if one of the values is true or the other one. So isAdmin has the binary representation of 00000001. I think that's enough zeros. 7 zeros followed by 1. Can see financials is going to end up with 100. Can see Europe is going to end up with the value 100000. And so when we OR those all together, we're going to get this byte that has these 3 flags set to true. So when we run this, we see that we've encoded 8 access roles for a user into a single byte of data. So we're able to store this information extremely efficiently. So if I want to see, for example, if this user is an admin, I can go ahead and print is admin and then print out the value. And then in order to determine if that's valid or not, then I can do a little bit of bitwise mathematics here. So I can take the constant isAdmin and that with the roles. And what that's going to do is that's going to apply what's called a bit mask. So only the bits that are set in the isAdmin constant and a roles are going to be left as true, which means if we're an admin, we're going to have the value 1 set at that first bit. And then I can compare that to the isAdmin constant. So when I run this, if we have the admin role, then we're going to get the value true. Now if I check something that I don't have the role, so let me go ahead and copy this down. And then let's just see if they're at the headquarters. So we'll put that in here. And it's exactly the same bitwise operations. We're just changing our mask. If we run this, we see that isHeadquarters equals false. Actually, let me put in my line return here and then run this again. And you see that isHeadquarters equals false. So we can very quickly and very efficiently store a lot of different information about what roles and access rights a user might have in a simple byte. And having this constant defined with this enumeration expression makes that really fast and really efficient and really clear in our application. Okay, so let's go into a summary and review what we've talked about in this video. Constants are another one of those foundational elements that's going to be a part of almost every application you're going to write. Now the first thing that we learned about with constants is that they're immutable, but they can be shadowed. So we can create a constant, we cannot assign a new value to it, but if we create a constant on an inner scope from an existing constant, then not only can we change the value, but we can even change the type, because that inner scope is going to shadow the outer scoped constant. They have to be replaceable by the compiler at compile time, so the value must be calculable. So we're not going to be able to access functions or command line arguments in order to determine the value of the constants in our application, but we are going to be able to do simple expressions like we talked about in the enumeration section. They're named like variables, so if you want to export the value of a constant outside of your package, then you're going to use Pascal casing, and if you want to leave it as an internal value to the package, then you're going to use camel casing to name that constant. Typed constants work just like immutable variables, so you can use them in arithmetic operations, you can pass them into functions, but they can only interoperate with the same type. Untyped constants have a little bit more flexibility, so they work just like the literals. So if you replace that constant throughout your application with the literal value of that constant, that's how it's going to work. So that's going to allow it to interoperate with similar types. So we had the value 42 defined as an untyped constant, and we could add that to an integer 16, we could add that to an integer, we can add that to a uint 16, any of those would work because the literal 42 will work in all of those cases. Then we talked about the enumeration types that we can work with, and we learned about the special symbol iota that allows us to start with the value 0 and increments one time every time we use it inside the same const block. Now the one thing that we have to watch out for is that constant values that match the 0 values of variables can cause subtle bugs in your application because you might have logic that you expect to initialize the value of the constant, and if something happens and that initialization doesn't occur, then you're going to be working with the 0 value, which might give you a false match to a constant that you're evaluating against. Using that iota operator, we can actually create what are called enumeration expressions. So we can define the value of the constant dynamically by combining iota with any arithmetic, bitwise operation, or bit shifting operation that's allowable with the primitive type that the constant is representing. I want to talk about the first two collection types that we have available in Go, arrays and slices. Now, arrays form the basis of slices, so I want to start our discussion with those. And when we talk about arrays, we're going to talk about how to create them, the built-in functions that Go offers us to understand what's going on with our arrays, and then we'll do some exercises working with arrays and see how we can use those in our applications. Then we're going to follow the same pattern, but we're going to switch over to slices. So we'll learn the various ways that we can create slices, we'll learn the built-in functions that we can use to understand what's going on with our slices, and then we'll do some exercises working with those. Okay, so let's go ahead and get started by learning how to create an array. So the first thing that I want to discuss about arrays is the use case for them. Why do we need them, and what are they used for? So let me just drop in an example. Let's just say that we're building an application that's going to work with the grades of students in a class. So without arrays, we're going to end up with an application something like this. We're going to have maybe grade 1, grade 2, grade 3, and then we can print out those grades. So we can go ahead and run this, and we see that we get the scores 97, 85, and 93 printed out. Now this works sort of, but we got a lot of problems here because our application needs to know exactly how many grades we have to work with at the time that we're designing the application, and working with these grades as a collection becomes very cumbersome. So enter the array, and that's going to solve all of our problems. So in order to see what an array looks like, let's go ahead and delete this code here, and then we'll create an array that's going to hold the grades for us. Now the way we declare an array is we're going to start with the size of the array. So we're going to use square brackets, and then we're going to have an index that's going to be the number of elements that our array can hold, and then the type of data that the array is going to be designed to store. So an array can only store one type of data. So in this case, we're declaring an array of integers that can hold up to 3 elements. If we wanted to hold a different type, say we wanted to have an array of strings, then we would type this to a string, and so on. So you have to specify at the time that you're declaring the array what type of data you're going to store. And then we can use this initializer syntax to put in the values for our array. So we can put in the same scores that we had before, 97, 85, and 93. And then if we come into our print statement here and add our grades as what we're going to print, then we see that we have all of the grades printed out together in this collection called an array. Right now, that's a convenient collector. As we start getting into looping constructs and things like that, we're going to really find that having things grouped into arrays and slices and the other collection types is a very powerful way for us to work with our data. Now, another advantage that we have with working with arrays is the way that they're laid out in memory. So if you declare 3 different variables and specify their values, it's impossible to know how they're going to be laid out by the Go runtime. With arrays, however, we know by the design of the language that these elements are contiguous in memory, which means accessing the various elements of the array is very, very fast. So by collecting our data together in arrays, not only is it easier to work with, but it also makes our applications generally a little bit faster. Now, one problem that we have in this example here is if you look at it, we're actually declaring the size of the array twice, because we have this syntax here where we're saying that we're creating a 3-element integer array, but then we're adding 3 elements to it. And that's not really required. If you're going to be initializing an array literal like we're doing here, then you can actually replace the size with these 3 dots here. And basically what that says is create an array that's just large enough to hold the data that I'm going to pass to you in the literal syntax. So in this case, we're going to get an array that has 3 elements in it, and that's implied by the fact that in this literal syntax, we've passed 3 integers to it. We can also declare an array that has a certain size, but has its values zeroed out by doing something like this. If we declare an array called students, and let's make that a 3-element array that's going to hold strings, and then let's print out what we have in that array. So if we print out students, make sure I'm spelling everything correctly and run this, then we see that we have an array that's empty. So we have declared a 3-element array that can hold strings, but obviously there's no elements in there right now. So in order to specify a value in the array, we're going to use this syntax. So we're going to call upon the array, and then we're going to tell it which index we want to work with within the array. So in this case, we're working with the 0th index of the student's array, and then let's just assign the name Lisa to it. And then we can go ahead and print out our array again and run it. And now we see that we have, I always forget to add this line return here. Then we see initially we have an array of students that's full of empty strings. In the second instance, we've actually specified that first element. Now you may be wondering why we're starting with the value 0. And the reason is related to how arrays are made up of contiguous blocks of memory. So when we talk about students as the name of the array, what Go is going to do is it's going to have a pointer, or it's going to remember the location of the beginning of that array. And then the index that we pass, in this case 0, is going to tell it how many strings to walk forward. So it knows that when it has a string has a certain length, and so it's going to walk that many strings. So when we pass 0, it's going to be the head of the student's array moved forward 0 string elements. And so that's going to be the first element of our array. So we can finish this example out. If I drop some code in here, we can see what it would take to fill out this array. So in this case, we got the 0th element is still Lisa, the first element is Ahmed, and the second element is Arnold. So if we print that out, we see the expected result where we have Lisa, Ahmed, and Arnold. And it doesn't matter what order we work with these. If we flip these around, then we find that they do flip around in the array. We can assign them in any order that we want. Now, if we want to add a specific element in the array, then we can use this square bracket syntax again and dereference the element from the array. So if we do this, and then change our label again, so we're going to get the second element of the array, which is index 1, then we can go ahead and run this, and then we see that the second element has the value Arnold. So we can use this square bracket syntax in order to assign values to the array, as well as to pull out the values that have been assigned. Now, another thing that we can do is we can determine how big the array is. Now, obviously, we created the array up on line 8, so we remember at design time that we created this, but there may be a situation where you need to go back and review the size of the array that you're working with. And the way that we can do that is using the built-in length function. So if I drop in another print statement here and format that, you see that we can get the number of students in an array using this built-in len function and passing in the array. So if we run this, then we see that we get the number of students equals 3, and that's going to print out the size of the array. So if we change the size of the array to, say, 5, then the results of printing out the array isn't going to change, but the size of the array does. Now, one thing that's important to remember is that an array can be made up of any type. It just always has to be the same type for a given array. So we've been working with arrays of integers and arrays of strings, so we've been working with primitives. But this example here shows that we can actually make up arrays of anything else. So in this case, we've got an array of arrays. So let's just say that we're working with some linear algebra, and we need the identity matrix, which is a concept that's used pretty often in linear algebra. So this array here stores a 3 by 3 identity matrix. So the first row is going to hold the values 1, 0, 0. The second row is going to hold 0, 1, 0. And the third row is going to hold 0, 0, 1. So if we go ahead and print this out, then we see that we do in fact get those values. Another way to look at this that may be a little bit easier to see is using this way here. So we're just going to declare the array of arrays, and then we're going to initialize each one of those rows individually. So this reads a little bit cleaner and might be a little bit easier for you to understand what's going on. And if we run this, we get the exact same result. Now, the last thing that I want to talk about with arrays is something that's a little bit different with arrays in Go than in other languages. And that is that arrays are actually considered values. So in a lot of languages, when you create an array, it's actually pointing to the values in that array. So if you pass things around, you're actually passing around the same underlying data. But in Go, that's not true. When you copy an array, as we're doing on line 9 here, you're actually creating a literal copy. So it's not pointing to the same underlying data, it's pointing to a different set of data, which means it's got to reassign that entire length of the array. So if I run this, you'll see what I'm talking about here. So on line 8, I assign an array. On line 9, I create another variable b and assign that to a. And then on line 10, I change the second element of the array to the value 5. And what you see is that when I print out the array a, it has the original values of 1, 2, 3, but b has the new values of 1, 5, 3. So when you're working with this, you have to be a little careful, because copying arrays, especially when we get into functions, if you're passing arrays into a function, Go is going to copy that entire array over. So if you're dealing with a 3-element array, that's not a big deal. If you've got 1,000,000 elements in your array, that could slow your program down a little bit. So what do you do if you don't want to have this behavior? Well, we haven't talked about it yet, but I want to give you a hint right now in order to cover this completely. And that is this idea of pointers. So the way that our program is working right now is that the value b is assigned to a copy of the array a. But if we do the address of operation, which is this character here, then what we're saying is b is going to point to the same data that a has. Now, we'll get into more detail about what this means later, but the long and the short of it is, if I run this, now a and b are pointing to the same data. So a is the array itself, and b is pointing to a. So when we change the value in line 10, we're actually changing the same underlying data for both. So when we print them out, we see that the array A has changed, as well as the array that B is pointing to, because they happen to be exactly the same array. Now, arrays are very powerful, and there's a lot of use cases where you can use arrays very efficiently. However, the fact that they have a fixed size that has to be known at compile time definitely limits their usefulness. So in Go, the most common use case for using arrays is to back something called a slice. So let's take a look at a slice. So the first thing that I want to do is comment out a couple lines in this example here. So we'll comment out this one, and this one, and then we'll change this over to slice syntax. So the way we're going to do that is simply by eliminating these 3 dots here. So a slice is initialized as a literal by just using the square brackets, the type of data we want to store, and then in the curly braces we can pass in the initialized data. So we go ahead and run this, we see that we get the values 1, 2, 3. It looks exactly like an array. And as a matter of fact, everything we can do with an array, we can do with a slice as well, with 1 or 2 exceptions. So in order to illustrate that, we had the length function that we talked about with an array. Well, we have the length function with a slice as well. So if I run this, we see that we do get the length of 3. So we initialize the slice with the values 1, 2, 3, so with 3 elements. So the length function gives us a value of 3. Now there's an additional function that we have available with slices, and that is the capacity. And that's because the number of elements in the slice doesn't necessarily match the size of the backing array, because the slice is really a projection of that underlying array. So we can have a very large array and only be looking at a small piece of it. Now if we run this example, we see that the capacity function returns a value of 3. So the underlying array is exactly the same size as the slice. But as we go along here, we'll see how we can get into situations where the length and capacity are different and why that's a very good thing. Now, unlike arrays, where we had this syntax here and we had to use this address of operation in order to point to the same data, slices are naturally what are called reference types. So they refer to the same underlying data. So if we run this example again, remember when we ran this with an array, we saw that B stored different data than A when we were done. So if we run this, we see that A and B are actually pointing to the same underlying array, and so when we change the value in B, we get a change in the value in A. So this is one thing that you're going to have to keep in mind when you're working with slices. If you got multiple slices pointing to the same underlying data, you have to keep in mind, if one of those slices changes the underlying data, it could have an impact somewhere else in your application. Now so far we've only looked at the literal syntax for creating a slice. And that's what we're seeing here on line 8. There's actually several other ways that we can create slices, and that is illustrated with this example here. So you see on line 8, we're creating a slice that has the values 1 through 10. And then on line 9, we're creating a slice B, and that's using this bracket with the colon in between. And what that's going to do is that's basically going to create a slice of all the elements of what it's referring to. So it's going to create a slice of all of the elements of A. On line 10, we're creating a slice C, and that's going to start with the third element of the parent and copy all the values after that. So that's going to start with the element with index 3, which is of course the fourth element, and every element after that. So this is going to copy 4 through 10 into the slice at C. Then on line 11, we're going to do the other syntax, and that's going to copy everything up to the 6th element, and that's the literal 6th element. That's not element number 7, that's actually the 6th element, which is going to have the index 5. And then on line 12, we actually see an inner slice. So we're going to copy the 4th element through the 6th element into our new slice. So let's go ahead and run this and see what prints out. So we see the first line printed out is the original slice that we have. The second line is the copy of that slice that's copying all of the elements. The third line is going to copy the 4th element on, so we see the number 4 through 10. The 4th line copies everything up to the 6th element, so we get the values 1 through 6. And then the last line printed out is a slice from 3 to 6, and so we're going to get the elements 4, 5, and 6 printed out. So that can be a little bit confusing because the first number has a slightly different meaning than the second number. So basically, the first number is inclusive and the second number is exclusive. So for example, if we look at line 12 again, we're going to copy from index 3 up to but not including index 6. So that's another way that you can look at it. Now one thing to keep in mind, remember what I said, that all of these operations point to the same underlying data. So if we take element 5 and change that value in the A slice and run this again, notice all of them change their value because they're all pointing to the same underlying array. So each one of these operations includes the 5th index in their results, and each one of those gets updated to the value 42. Now another thing to know about these slicing operations is they can work with slices like we're doing here, but they can also work with arrays. So if you remember, if I put these 3 dots in here, it's actually going to turn A into an array. And if I run this, we get the same result. And that's because slicing operations can have as their source an array or a slice. So whatever type of data you're working with, as long as it's one of those two, you can use these slicing operations. Now the last way that we have available to us to create a slice is using what's called the make function. And that's a built-in function that we have to work with. So if I delete all this and drop this guy out, we're going to use the built-in make function, and this takes 2 or 3 arguments. So let's start with 2 arguments. So the first thing we're going to say is the type of object that we want to create. So you can use make for several different operations. In this case, we're going to be talking about making slices. So in this example here, we're going to make a slice of integers. The second argument is going to be the length of the slice. So in this case, I want to start with 3 elements. So now let's just get some information about the slice that we created here. And we'll do that by dropping in a couple of print statements. So we'll print out the values of the slice, the length of the slice, and the capacity of the slice. So if I run this, no big surprise, it's zeroed out. So when I create a slice, everything gets set to the 0 value, which is what we always expect in Go to happen. Every time we initialize a variable, we expect it to be initialized to the 0 values. And that's true for slices just like it's true for primitives. When we ask for the length, we get a length of 3. When we ask for the capacity, that's also set to 3. Now we can also pass a third argument to the make function, and that's going to set the capacity. So keep in mind, the slice has an underlying array, and they don't have to be equivalent. So if we run this, we see that we've created a slice of length 3. It's got 3 elements in it, but the underlying array has 100 elements in it. So why would we do that? Well, the reason is because, unlike arrays, slices don't have to have a fixed size over their entire life. We can actually add elements and remove elements from them. So in order to show you an example of that, let me drop in another example here. And this is going to start with a slice of integers that starts with no elements in it. So if we go ahead and run this, we see what we expect. We see an empty slice, length of 0, capacity of 0. Now if I want to add an element to this slice, I can use the built-in append function. So this takes 2 or more arguments. The first is going to be the source slice that we're going to be working with. So I'm going to start with A, and I'm going to add an element to it. And in this case, all I want to do is add the number 1 to it. And then let's go ahead and print out the value of the slice, the length of the slice, and the capacity of the slice again. So if I go ahead and run this, we see that in the second operation, we have a value 1 stored in there. We have the length of 1, and notice the capacity is 2. So that's kind of interesting. What happened here is when we initialize the slice to the value A, Go assigned a memory location for the slice. And since it didn't have to store anything, it basically created an underlying array of 0 elements for us. As soon as we added an element, obviously it couldn't fit in a 0 element array. So it had to assign an array for us. So what Go does is it copies all of the existing elements, in this case nothing, to a new array that's got a larger size. So when we reassigned, it actually did create a new array. This one has a capacity of 2, and then it put the value 1 into that array. Now, when we're dealing with small slices like this, things are pretty cheap and pretty easy, even if you're resizing the array quite a few times. However, as things get very large, these copy operations become very expensive. And that's why we have that 3-parameter make function. That way, if we know the capacity is going to be somewhere around 100 elements, you can go ahead and start there, and that way, as you're appending elements and building up the slice, you're not constantly copying the underlying array around. Now, if you remember, when I said the append function can take 2 or more arguments, the reason for that is this is what's called a variadic function. So everything after the first argument is going to be interpreted as a value to append to the slice passed in the first argument. So if we have this example here, we're actually going to append the values 2, 3, 4, and 5 to the slice returned by A. So if we run this guy, we see that we get the elements 1 through 5 created there, and the length is 5, like we might expect, but now the capacity is 8. Now, it's not fixed in stone how Go resizes the arrays, but generally what I've seen it does is once it fills up the underlying array with a slice, when you add the next element, it's going to create a new array, and it's actually going to double the size from the previous array. So if we start with an empty slice, we see that the array would initially be of size 0, then it'll go to 2, 4, 8, 16, 32, and 64 elements. So that's something else to be aware of. If you're just over one of those powers of 2, you can actually end up with a lot of memory consumed that you're never going to be using. So again, if you have the ability to come up with a decent first estimate, then that's going to be beneficial to you. Now, one common situation that you're going to run into is if you have a slice of elements and another slice of elements, and you want to concatenate them together. So you want to have another slice created that has all of the elements of the first slice and all of the elements of the second slice. So you might want to do something like this. If I convert this over to a literal slice, you might want to run a command something like this. Well, this unfortunately is not going to work. If I go ahead and run this, you see that we're going to get Go complaining to us, and that's because the second argument to the append function has to have the type of the slice. So Go can only accept integers here. It can't accept a slice of integers. But we do have a way around this. So I don't know what it's called in Go. In JavaScript, they would call this the spread operator, where if you had 3 dots after the slice, it's actually going to spread that slice out into individual arguments. So if we run this, this is going to work, and it works exactly the same as if this weren't a slice at all. It's basically going to take the slice and decompose it into looking something like this. So these work exactly the same way, but it's a convenient feature to know about if you have slices and you want to concatenate them together. Now, some other common operations that you might do with slices are stack operations. So let's just say that we're treating our slice as a stack and we want to be able to push elements onto the stack and pop elements off of the stack and things like that. Well, the append function is going to allow us to push elements onto the stack, but how do we pop elements off? Well, we have a couple of different ways that we want to do this. If we want to do what's called a shift operation, which means we want to remove the first element from the slice, then we can do this operation here. And what this is going to do is it's going to create a new slice that starts at index 1, which is the value 2 in this example, and takes everything else from that. So if we go ahead and print out the value of b, we'll see that that has the elements 2 through 5. Now, if you want to trim an element off of the end, then you're going to have to use a different syntax here. So we want all of the initial elements, so we're going to start with a colon, and then we'll use that length operation, figure out the length of the slice, but remember, that's going to return a number that's too large. We actually want to remove an element off. So let's go ahead and do length minus 1, and this will have the values 1 through 4 in it. So it's pretty easy to remove an element from the beginning of the slice or the end of the slice, but what happens if you want to remove an element from the middle? Well, here things get a little bit hairy, because what we have to do is we actually have to concatenate 2 slices together. The first slice is going to be all the elements up to where we want to remove the element. So in this case, we can take the first 2 elements by doing a slice of A and passing in colon 2 for the slice that we want to create. Then we have to concatenate to that all of the elements after the index we want to remove. So in this case, we're removing that middle element. So we'll take from 3 on, and then we have to use this spread operation in order to spread things out so that the append function is happy. So let's go ahead and run this, and then get my syntax correct here. And now we see that we've got the elements 1, 2, 4, and 5. So we've successfully removed an element from the slice. Now you have to be a little bit careful here, because keep in mind, we're working with references to the same underlying array, because these are all slicing operations. There's one underlying array, and everything is being done on that underlying array. So just to show you the havoc that we've created here, let me go ahead and print the value of A out here, and then print the value of A out afterwards, and go ahead and run that. And you see we start out with the elements 1, 2, 3, 4, 5, like we might expect. We do our slicing operation, removing the element from the middle. We get 1, 2, 4, 5, which was what we might expect. But then when we print A out, things look a little weird, because we have that slice that B represents, which is 1, 2, 4, 5. Our 3 is completely gone, and 5 is duplicated. So this is something to be very sensitive about. If you're going to be removing elements from the inside of a slice, using a command like we have on line 10, make sure that you don't have any other references to that underlying array. Otherwise, you're going to get some unexpected behavior. So what do you do if you have a situation like this and you really, really need A to stay the same and you really, really need B to change? Well, unfortunately, we don't have the tools to work with this right now, because what we're going to need to do is use a loop to create a copy of that slice that doesn't point to the same underlying array, and then you can make the manipulation. So when we get to the looping section, we'll show you how to do loops, and then you'll have all the tools that you need in order to handle that situation. For now, the only thing I could say is beware of this behavior. And if you get into a situation like this, understand that you're going to have to do a little bit of research in order to make sure that your application responds correctly. Okay, so that covers what I want to talk about with arrays and slices. Let's head into a summary and review what we've talked about. Arrays and slices are very common in Go applications, and I think you're going to see them all over the place as you start to work more and more with the language. So I hope that this conversation has really helped you understand what arrays and slices are and some basics about how you can work with them. We started our discussion by talking about arrays, and we learned how they're collections of items with the same type. So you can't create an array that has strings and integers and things like that. All of the types have to be the same, but it does collect them all together. And as we start to get into conversations about looping and things like that, we're going to find how we get some very powerful tools that we can work with when we're basing our data on arrays and slices. They are fixed size, so when you create an array, you have to specify at compile time how big that array is, and it can never change. So you can't make them smaller and you can't make them larger. There are three different ways that we can declare an array. We can do the literal style like you see on this first line, where we're going to specify the number of elements, and then we use a literal that's going to initialize those elements. However, we do have a shorthand notation that uses 3 dots instead of that first size, and that's going to be a little bit more robust in your application design, because if you run into a situation where you need to add another literal, you don't have to remember to update the size of the array. It's going to update automatically. We also have this third syntax where we can declare a zeroed out array. In this case, we're going to declare an array of 3 integers. Each one of those integers is going to start with the value 0. We also talked about how arrays are zero-based. So we're going to be counting from the head of the array. So the first element in the array has the index 0, the second element has the index 1, and so on. So in this example, if we ask for the index 1 of array A, we're going to get the value 3 out. We have the len function that's going to return the size of the array in case you need to know that some other place in your application, and you want to have a way to be able to handle that robustly that's not relying on the fact that you know at design time how big that array is. You can use the len function to interrogate the size of the array. Anytime you're moving the array around, it's going to copy the underlying data. So if you have a 3-element array and you assign that to another variable, all 3 elements are going to be copied to a new location in memory, and you're going to be working with an independent copy. So that can cause some unexpected behaviors, because if you change that copied array and you expect the changes to be reflected back in the initial array, that won't happen. And it can be very expensive because all that memory has to be allocated a second time. Then we moved on to discuss slices and how they're very similar to arrays. As a matter of fact, they're backed by an array. So every slice that you see under the covers, Go has an array that's holding all of that data for you. There are several creation styles. We saw that we can create a slice by slicing an existing array or another slice. We have the literal style that we can use, which is very similar to the array literal, except for we just leave those 3 dots out because the size of the slice is dynamic, and so it can be determined at runtime. We also saw how we can use the make function. So if we pass 2 arguments to the make function, the first is going to be the type of slice that we want to create. So in this example, we're going to create a slice of integers, and the second parameter is going to determine the length and the initial capacity of the slice. If we need a capacity that's different than the initial length, then we can pass a third parameter into the make function, and that's going to allow us to specify a capacity independent of that initial length. The len function returns the length of the slice itself, whereas the capacity function returns the length of the underlying array. So if, for some example, you want to control the resizing of the slice, you can go ahead and do that, and use that capacity function to understand when you're starting to get to your limits. You can also use the append function to add an element to the slice. Now what that's going to do is it's going to take in a parent slice, and it's going to take in 1 or more elements to add to that slice. Now through the course of that append operation, you can add elements that exceed the capacity of the underlying array. If that happens, then you are going to trigger a copy operation, and all of those elements are going to have to be copied to a new location. So be aware of that. If you're dealing with large slices of data and you end up resizing a lot of times, your application performance can suffer. You might want to think about using that 3-parameter make function in order to set the capacity of the slice close to where you need it to be. When you're passing slices around in your application, keep in mind that assigning a new value to an existing slice actually points to the same underlying array. So if you manipulate the slice in one location, it's actually going to affect all the other slices that are pointing to that same underlying data. So we talked about an example where we created a slice and removed the middle element out of it, and we saw how that actually affected the initial slice and could cause some behavior that we weren't expecting. I want to complete the discussion I started in the last video by talking about the 2 remaining collection types that are available in Go, and those types are maps and structs. So we'll start our discussion by talking about maps. We'll talk about what they are, how we can create them, and then how we can manipulate the data within the maps. Then we'll move on to the struct data type. We'll talk about what they are, how we can create them. Then we'll move on to the naming conventions that we're going to have to be aware of as we're working with structs. Then we'll talk about a concept called embedding and how we can use that to have a struct that we're creating inherit a lot of functionality from a base struct. Then we'll finish our discussion of structs by talking about a concept called tags and how we can use tags to provide some additional information about the fields within our structs to help the consumers of objects created from the structs get additional information about how that field is intended to be used. Okay, so let's begin our discussion by talking about what maps are and how we can use them. So the first thing that we're going to need to get our heads around when we're talking about maps is what exactly a map is. And I think the easiest way to show you what a map is by showing you a map. So we have an example here of a variable called state populations, and this represents a map of U.S. state names over to the population within those states. So what we see here is a map is going to take some kind of a key, in this case the state names, and it's going to map that over to some kind of a value, in this case the population of that state. So what this provides us is a very flexible data type when we're trying to map one key type over to one value type. Now there's a couple of constraints we're going to have to keep in mind. As you can see up in the declaration on line 8, we're going to map one key type to one value type. So all of the keys in this map have to be of type string, and all of the values have to be of type integer. Now we can use a lot of different types for the keys, and we can use any type for the value, but when we declare a map, that type has to be consistent for every key value pair within the map. So if we run this, we can see an example of what a map looks like when we print it, and it's not the best output in the world, but we can get an idea of what's going on. So we see that we get the key value pairs printed out, so we get California, Texas, Florida, New York, Pennsylvania, Illinois, and Ohio. So one thing that I just alluded to is that we have a lot of options with the key type, but we don't have an infinite number of options. So the basic constraint on the keys when you're creating a map is they have to be able to be tested for equality. Now most of the types that we're working with can do that. So booleans can be tested for equality, all of the numeric types, strings, pointers, interfaces, structs, arrays, and this thing we haven't talked about called channels. All of those can be tested to see if one instance of, for example, a string variable is equivalent to another one. However, there are some data types that cannot be used for equivalency checking, and those are slices, maps, and other functions. So for example, if we create a map called M, and we'll make that a map of, say we want to map slices of integers over to strings, and we'll use the literal syntax for that, and then we print that out, then you would expect a map to print out. But in fact we get an error because we've got an invalid key type because a slice cannot be a key to a map. However, if we add an index here, then it turns it into an array, and now we do get a successful printout. Of course the map is empty, so we don't see anything, we just see this empty map right here, but we were successfully able to create the map because an array is a valid key type, but a slice is not. So what are the different ways that we can create a map? Well, you see the first way here. This is the literal syntax, and this is going to probably be the most common way you're going to see maps created. So we just need to declare the type of the map, and we're going to do that using this syntax that we see here on line 8, where we're going to start with the map keyword. In square brackets, we're going to list the type of the key, and then after the square brackets, we're going to list the type of the value. Another way that we can do this is we can use the built-in make function again. Now we first saw the make function when we were talking about slices, but we can use that once again here. So if I copy this variable up here, and I set this equal to the result of calling the make function, and we're going to tell it what type of map we want to make. So we're going to use the map keyword again, the key is type string, the value is type integer, and now we can go ahead and remove this colon, and if we run this, we have to remove our M again from our print statement. Now if we run it, we get the same value printed out. So this is a common way that you can work with maps if you don't have, at the time that you're declaring the variable, the entries that you're going to want to put in it. So for example, if you're populating the map within a loop, you might use this syntax. Now another option that you have with the make is it will take a second parameter. So if I run it like this, then that works. However, I wasn't able to find the intention for this. So this is available, but it doesn't seem to affect the length of the map that's created. The map is always going to be the length of the number of elements in it, but it might have some effect under the covers. If you find out what that's for, please leave a comment down below so that I can learn along with you. Now let me go ahead and remove this because I don't know what it's there for, and I haven't seen that very commonly used, and run this again, and we can see that we're back to where our map used to be. Now, how are we going to manipulate the values in our map? Well, the first thing that we can do is we can pull out one single value from the map by using the square brackets and typing in the value of the key. So the key can be provided either as a variable or, as I'm doing here, as a literal. So if I go ahead and run this, we see that we get the population of Ohio is 11.6 million people. So we can interrogate the values of our map using this syntax here. We can also add a value to our map using a very similar syntax. So if we call on the state populations variable and I add a key, in this case let me add the next largest state, which is Georgia, and it, as of 2016, had a population of 10,310,371. Now I can pull that value back out, run this, and we see that we get that value printed out of our map. If we print the entire map out, we see right here Georgia gets added in here. Now, something you might have noticed, let me do this. I'm going to copy this print line here, put it above where we added the Georgia key, and notice the ordering is different. And this is going to be a very important thing to keep in mind as you're iterating through maps later on. The return order of a map is not guaranteed. So even though we declared California, Texas, Florida, New York, Pennsylvania, Illinois, Ohio, and then added Georgia, this is not like a slice. A slice or an array would return those elements in exactly the same order we provided them. In a map, everything is stored in a way that cannot guarantee the order upon returning. So even though we just added one entry here, it completely changed how everything was organized within the map, and we get a little bit different output. Now, another thing that I want to show you is that we can delete entries from a map. So we can do that using the built-in delete function. The first is the map that we want to delete from, and then we need to provide the key that we want to delete. So if we go ahead and delete Georgia back out, it wasn't there very long, but if we run it, looks like I need to add my S here. Now if we run it, we see that Georgia is no longer part of our map. So we can add by just calling on the map, providing a new key and value. We can delete using the built-in delete function, and we can interrogate a value from the map using those square brackets. Now, an interesting thing about deleting is if I ask for the value of that key again, what do you think I'm going to get? So we see here in the output, Georgia is no longer part of the map. So you might expect some sort of error to be raised. Well, in fact, if I run this, we get the value 0 out. Now that should cause you some concern, because does Georgia have a population of 0? Or is it missing from our map? Did I just misspell the key? What's going on? So for example, if I fat finger Ohio and I forget the I and run this, I get a value of 0. Well, did everybody move out of Ohio? What happened? Well, with what we know right now, there's no way for us to really know. So there's another way that we can interrogate our map, and that is using what's called the comma OK syntax. So with doing what we know right now, we're basically doing this. We're calling state populations, and we're asking for the key Ohio, and I'll continue that misspelling, and then we're printing out the value of that population variable, and we get the value 0. Well, we can also add an optional comma OK here, and when we do this, let's go ahead and add that OK variable to the output and see what that's going to do. So notice that this prints out the value false. So the OK is false if the key was not found within our map, but if we add the I back in and correct our spelling, we see that we get the value true out. So if you're in a situation where you're not sure if the key is in the map or not, then you can use this comma OK syntax. As a matter of fact, if you just want to check for presence, then we can use that write-only operator again in order to throw away the actual value, and then we just get the OK variable printed back out. Now there's nothing magic about the variable name OK, but it is conventional to use OK in your Go programs when you're using it for this kind of a test. The next thing that I want to show you about maps is we can in fact find out how many elements are in them. So we can do that using the built-in len function. So if I go ahead and run that, we see that we get the value 7, and we have, let's see, 1, 2, 3, 4, 5. Yep, we have got 7 states declared in our map right now. So if we added another state back in, then the length function would return 8. The other thing that's interesting to know is that just like slices, when you have multiple assignments to a map, which is especially important when you're passing maps into functions, the underlying data is passed by reference, which means manipulating one variable that points to a map is going to have impacts on the other one. So I can demonstrate that by creating another variable called SP and set that equal to state populations. And then let's go ahead and delete poor Ohio out of SP. It always seems to get left out. And then we can print out SP and print out state populations. So if I run this, we see that in our first result, we don't have the entry Ohio anymore, and in our second print statement, which is the original map, Ohio's been removed from there as well. So if you start passing maps around and you start manipulating the data within that map, keep in mind you can't have side effects on the calling functions or any other place where that map is referred to, because manipulating the map in one place is going to have impacts on every other place it's used. So the final collection type that I want to talk about today is called a struct. Now at first, you might not think of a struct as a collection type, but go with me on this. If I drop in an example, we see here an example of a struct. Now I'm in kind of a Doctor Who frame of mind today, so we're going to run with an example that's talking about some information about one of the doctors from Doctor Who. So if I go ahead and run this, we can see that we're getting information on the third Doctor. The actor's name is Jon Pertwee. We see some of his companions listed out here. So the reason I call this a collection type is look at the declaration of the struct on lines 7 through 11. What we have here is a list of field names. So we've got number, actor name, and companions as field names, and then a type associated with that field. So the doctor number is an integer, the actor name is a string, and the companions is a slice of strings. So what the struct type does is it gathers information together that are related to one concept, in this case a doctor, and it does it in a very flexible way, because we don't have to have any constraints on the types of data that's contained within our struct. We can mix any type of data together, and that is the true power of a struct. Because all of the other collection types we've talked about have had to have consistent types. So arrays always have to store the same type of data, slices have the same constraint, and we just talked about maps and how their keys always have to have the same type, and their values always have to have the same type within the same map. When a struct, we can have our fields describe any type of data that we want. So we can have structs that contain other structs, anything that we want. So while in a lot of ways structs are the simplest type of collection that we're going to be talking about, they're also one of the most powerful. So we see down here in the main function how we can create a struct, and I'm using the declaration syntax where I'm using named fields. So we're going to create a variable called aDoctor, and we're going to use this literal syntax. So we list the type of the struct, doctor, we use the curly braces like we do with every other literal definition, and then I have a list of the field names, colon, and the value. So number, colon 3, actor name, colon Jon Pertwee, and then companions is set equal to this slice of strings. Now notice that when I'm setting something equal to a slice, I do actually have to tell Go what kind of collection type I'm initializing for that. And then down here on line 23, I go ahead and print the entire value of the struct out, and you see that I get the values printed out. I see 3, Jon Pertwee, and then the 3 companions that Jon Pertwee had in his time as the doctor. Now if we want to interrogate one value from a struct, then we're going to use what's called the dot syntax. So if we ask for the actor name of this struct, then we're going to put a dot after the variable name, put in the field name, and when we run this, we see that we get Jon Pertwee out. So we can work with the struct as a whole, or we can start drilling down. As a matter of fact, we can drill down through the structure. So if we ask for the companions, we can get that out, certainly. But this is a slice like any other slice. So if I just want the second item in the collection, I can get Joe Grant out by interrogating the slice that gets returned by asking for the companions field. Now another way that we can instantiate our structs is using what's called the positional syntax. So here I'm listing the field names, but I don't have to. So if I go ahead and take these out and take this out, so I print the entire struct out, then I get exactly the same result as I got the first time. Now this is valid Go syntax. I would encourage you not to use it though. And the reason for that is it can become a maintenance problem. So for example, let's just say that this is our struct and this is checked into source control and everybody's happy with it. But then let's say we have a change request come and we're going to add a list of the episodes that each doctor appeared in. So that's going to be another slice of strings, and that gets added right here. Well, if we use the positional syntax and try and run this, we've got a problem, because Go doesn't know how to map the fields that we provided into the initializer, because there's 3 values provided in the initializer and there's 4 values in the struct. So we have to find every place that we have one of these declared with the positional syntax, and we have to add, for example, a placeholder or populate it or something. So we go ahead and run this and everything's working again. But now what happens if another change comes along and somebody does this? Now they've changed the order of the fields. When we run this, everything looks fine, but when I ask for the doctor's companions again, I get an empty slice, because the positional syntax requires the fields to be declared in the correct order. Much better for us to go ahead and add in the field names. So let me drop those in real fast here. Now when I run this, I get the expected results out. And notice with the field name syntax, I don't even have to have it in the same order as they're declared in the struct. Go is going to figure out how to map the data from the initializer over into the object that's created by using those field names. The other advantage that I have is if I don't have any information about the episodes at this point in my program, I actually can ignore the fact that that field exists. And what this means is I changed the underlying struct without changing the usage at all, which makes my application a little bit more robust and change-proof. So, while it is possible for you to use the positional syntax, I would strongly recommend you do not use it unless you've got a very short-lived struct. We'll talk about anonymous structs here in a second, and in those situations, positional declaration might make sense because that struct is not going to live for very long. However, I would strongly recommend anytime you're taking the time to declare a type like we're doing here on line 7, then you're generally going to be better served by using field names explicitly instead of the positional syntax. Okay, the next thing I want to talk about are naming conventions. So as you can see here, I've got my type declared as doctor with a capital D and the fields declared as lowercase. So the rules in this situation follow the rules for any other variable in Go. If we start with a capital letter, it's going to be exported from the package. If we start with a lowercase letter, it's going to be internal to the package. So in this case, I can work with all of the fields because I'm declaring the doctor type in my main package. And so my main function, which is also in the main package, has access to it. However, nothing in any other package would have access to this. So it would be able to see that there is a doctor struct, but it wouldn't see any field names. So if I did want to publish these out so anything can use them, I would have to go ahead and capitalize these field names. Of course, I'll have to capitalize them in my declaration as well. And then when I run, I get the exact same result that I got up before, except for I've got to change this variable as well. Go ahead and run that, and I get the expected result out. So generally, we're going to follow the same convention as we do with any other variable. Uppercase is going to export, lowercase is going to import. You should use Pascal casing and camel casing. You shouldn't have underscores and things like that in your field names or in your struct names. Now, if you notice here on line 7, I have explicitly created a type called a struct. And that's going to be a very common way that you're going to see structs used. So you're going to define a type, and then everywhere you need to use that struct, you can just refer to it by its type. But we don't have to do that. And there are some situations where you might see a program like this. So on line 8, we're declaring what's called an anonymous struct. So instead of setting up a type and saying doctor, and that's going to be a struct, and that's going to have a single field called name that's going to take a string, we're condensing all of that into this single declaration right here. Now, I can't use this anywhere else because it's anonymous, and so it doesn't have an independent name that I can refer to it, but I can certainly use this just fine. So let me go ahead and delete this, and then notice I'm using the initializer syntax right here. So we got 2 sets of curly braces. It's very important to remember what each one is doing. So the first set of curly braces is paired to the struct keyword, and it's defining the structure of the struct. The second is the initializer, and it's what's going to provide data into the struct. So if we run this application, we see that we do get the struct with the value John Pertwee printed out, and everything's going to work just fine. Now, when are you going to use this? This is going to be used in relatively few situations. Basically, you're going to use this in situations where you need to structure some data in a way that you don't have in a formal type, but it's normally only going to be very short-lived. So you could think about if you have a data model that's coming back in a web application, and you need to send a projection or a subset of that data down to the client, you could create an anonymous struct in order to organize that information so you don't have to create a formal type that's going to be available throughout your package for something that might be used only one time. Now, unlike maps, structs are value types. So if I take this example here, and let's just use the same basic manipulation that we've been doing with all of these collections. So I'm going to create another struct, and I'm going to assign it to the value of my current struct, and then I'm going to manipulate the value of that name field. So I'm going to create another doctor called Tom Baker, and then let's see what happens when we print both of these doctors out. So as you can see, even though I copied another doctor from a doctor and changed the values remain independent. So a doctor still has the name John Pertwee, another doctor has the name Tom Baker. So unlike maps and slices, these are referring to independent data sets. So when you pass a struct around in your application, you're actually passing copies of the same data around. So if you've got structs that are very, very large, keep in mind you're creating a copy every time you're manipulating this. Now, just like with arrays, if we do want to point to the same underlying data, we can use that address of operator. And when we run this, we have in fact both variables pointing to the same underlying data. A doctor is the struct itself. Another doctor is a pointer to the struct. So when we manipulate its name field, we're actually manipulating the name field of the a doctor struct. The next thing that I want to talk to you about in Go is a concept called embedding. Now, you may have heard in your research on the Go language that Go doesn't support traditional object-oriented principles. So for example, we don't have inheritance. And oh my goodness, how am I going to create my program if I don't have inheritance available? Well, let me show you what Go has instead of an inheritance model. It uses a model that's similar to inheritance called composition. So where inheritance is trying to establish the is a relationship. So if we take this example here, if we were in a traditional object-oriented language, we would want to say that a bird is an animal, and therefore a bird has a name, a bird has an origin, a bird has also bird things like its speed and if it can fly or not. Go doesn't support that model, but instead it supports composition through what's called embedding. So right now we see that animal and bird are definitely independent structs. There's no relationship between them. However, I can say that a bird has animal-like characteristics by embedding an animal struct in here like this. So I've just embedded the struct itself. I haven't provided a name. Now if I did something like this, then I would have a named field in the bird called animal. But I'm not doing that, I'm doing this. So I'm just saying embed the animal struct right into the bird struct. Now how can I use this? Well, let me drop in a new main function here, and then you can see. So I'm creating an instance of a bird, and then I'm initializing the variables. So name is going to be emu, origin is going to be Australia, the speed is 48 kilometers an hour, and it cannot fly. So if I print this out, I see that, other than a little bit of a strange syntax with that inner type, I see that I have all of my fields defined. As a matter of fact, I can come in here and dig into any one of those animal fields, and everything works exactly like I would expect them to. So it kind of looks like bird is inheriting the properties of animal. But really what's happening here is there's some syntactic sugar. Go is handling the delegation of the request for the name field automatically to the embedded animal type for you. So if you try and pass these around and look to see if the bird is a type of animal, it is not. Bird is still an independent struct that has no relationship to an animal other than the fact that it embeds it. So it's not a traditional inheritance relationship where a bird is an animal. Instead, it's a composition relationship, which is answering the question, has a. So a bird has an animal or has animal-like characteristics, is how we would say it in this example, but it is not the same thing as an animal. They cannot be used interchangeably. In order to use data interchangeably, we're going to have to use something called interfaces, which we'll talk about a little bit later. Now we can see in this example that if we declare the type and we initialize the variables afterward, everything's pretty clear. We can just treat all of the fields as if they're owned by the bird struct, and we don't have to worry about the internal structure of the struct, and that's very intentional. However, if we're going to use the literal syntax, we do have to know a little bit about the bird's internal structure. So let me drop in this code here, clean up our formatting a little bit, and then remove these lines here. So this is declaring exactly the same object. We're going to have an emu from Australia. The speed is actually going to be 48 kilometers an hour, and can fly is going to be false. But notice what I have to do here. I have to explicitly talk about the internal animal struct. So when I'm working with the literal syntax, I have to be aware that I'm using embedding, but if I just declare the object and manipulate it from the outside, I don't have to be aware of it at all. Now, when should you use embedding? Well, I will say, generally, if you're talking about modeling behavior, embedding is not the right choice for you to use. When we get into methods, we will see that embedding will allow behaviors or methods to carry through into the type that has the embedding. However, the fact that we can't use them interchangeably is a very severe limitation. Generally, it's much better to use interfaces when you want to describe common behavior. So when is embedding a good idea? Well, if you're authoring a library, for example, and let's just say you're making a web framework and you've got a very sophisticated base controller. In that case, you might want to use consumers of your library to embed that base controller into their custom controllers so that they can get useful functionality out of it. In that case, you're not talking about polymorphism and the ability to interchangeably use objects. You're just trying to get some base behavior into a custom type, and in that case, embedding makes sense. The last thing that I want to talk about with structs is a concept called tags. So let me just drop in another example program here that we can work with. This is a simpler version of what we had before because we don't need two structs for this conversation. So we're just going to have a simple animal struct with the name and the origin fields. And then what I want to do is I want to add what's called a tag in order to describe some specific information about this name field. So let's say, for example, that I'm working with some validation frameworks. So let's just say that I'm working within a web application and the user's filling out a form and two of the fields they're providing are the name and the origin. And I want to make sure that the name is required and doesn't exceed a maximum length. So I can do that with a tag that looks something like this. So the format of a tag is to have backticks as the delimiters of the tag, and then we have these space delimited key value pairs. So my first field is going to be required, so I'm going to say that the name field is required, And then I've got a max length argument, which in this case is set to 100 characters. So the value of the tag is arbitrary. You could actually put any string that you want in here, but this is the conventional use within Go. We're going to use space-delimited subtags, and then if you do need a key-value relationship, then you're going to use a colon to separate the key and the value, and then the value is typically put in quotation marks. So now that we have this, how do we get at it? Well, the way that we're going to get at it is using Go's reflection package. So there's no straightforward way from an object to get at the tags of a field. You have to use reflection in order to get that. But fortunately, Go makes this pretty easy. So the first thing that I need to do is I need to get the type of an object that I'm working with. So I get that using the reflect package's type of function, and I have to pass in an object to this. So I will just initialize an empty animal to get that, and then I can grab a field from that type using the type's field by name method, and then passing in the name. In this case, I want the name. And now I can get at the tag by asking for the tag property of the field. So if I run this, we see that I do in fact get that tag out. Now what do I do with that? Well, that's really up to my validation framework to figure out. All tags do is provide a string of text, and something else has to figure out what to do with that. So this tag's value is meaningless to Go itself. We're then going to have some sort of a validation library that's going to have to parse this, figure out that yes, required is part of the tag, and then it's going to have to decide, well, if required is there, then I'm going to apply this logic, making sure the string is non-empty or whatever makes sense in our use case. Okay, so that finishes up what I have to talk about with maps and structs. Let's go into a summary and review what we've talked about. In this video, we talked about the two remaining collection types that are available in Go. We talked about maps and we talked about structs. Now, when we talked about maps, we learned that they are collections of value types that can be accessed by keys. They can be created as literals or via the make function, and members are accessed via the square bracket key syntax. We can check for the presence of an element within a map using this OK syntax. So we can ask for the value, add a OK, and what the map is going to return is the value type as well as a Boolean that's going to indicate if the value was found or not. Now, if the value wasn't found, your value variable is going to be the 0 value of the value type in that map. So for example, if you've got a map of strings to strings and the element isn't found, you're going to get an empty string returned out. If you've got a map of strings to integers, for example, you're going to get the value 0. If you have multiple assignments to the same map, they all point to the same underlying data. So they're what are called reference types, which means that if you manipulate the data in a map in one location, any other variables that are pointing to that same map are going to see that change as well. We then went on to talk about the struct type and how they're a collection of disparate data types. So whereas arrays and slices and maps are all collecting the same data type together, a struct is unique in that it collects any type of data together. So you've got a common field name, but those fields can point to any valid data structure within Go. They're keyed by name fields, which generally follow the syntax of any valid variable, including whether they're exported or not. So if you capitalize the name of a field, then that's going to be exported from the package. If you leave it lowercase, then that's going to be kept internal to the package. They're normally created as types, but we can create anonymous structs if we need to. And again, common use cases for this are very short-lived structs, such as generating a JSON response to a web service call that's only used one time. Structs are value types. So if I assign a variable to an existing struct, then all of the struct's values are going to be copied over to create a brand new struct. So if I manipulate a struct in one location, it's not going to affect any other variables in your application. We don't have an inheritance system within Go, but we can use composition using what's called embedding. So when we want to embed one struct within another, we just list the type of the struct and we don't give it a field name. Go is then going to automatically interpret that for us and delegate any calls for fields or methods in the containing struct down to the embedded struct if that top level struct doesn't contain a member with that name. We also learned a little bit about tags and how they can be added to struct fields to describe that field in some way. So there's a lot of different use cases for this. The JSON package uses this to provide ways to map field names from Go field names, which are typically uppercase, to follow JSON conventions, which are typically lowercase. We also saw that we can use this, for example, to pass information into a validation framework, and that framework could generate errors if we need fields to be required or have rules about their length or things like that. I want to start a discussion about the tools that Go makes available to control the flow of execution in our applications. In today's video, we're going to focus on two of these tools, the if statement and the switch statement. We'll start our discussion by talking about if statements, and we'll talk about all of the different ways that we can use them in our applications. And we're going to specifically focus on the various operators that are often associated with working with if statements, and we'll go through what those are and how you can use them. And then we'll talk about the relatives of the if statement, and those are the if-else statement and the if-else-if statement. We'll then move on to talk about switch statements, and we'll start that conversation with some simple use cases for switch statements. We'll then talk about cases with multiple tests, how we can fall through from one case to another in our switch statements, and then we'll talk about this special version of a switch called a type switch. So let's go ahead and jump in and start learning about if statements. In order to start our discussion about if statements, I want to start as simply as we can. So if you look at this application here, it's got just about the simplest if statement that I could come up with. So we're going to start with the if keyword, as you see here on line 8, and then we're going to have an expression that generates some kind of a Boolean result. And that's actually where we're going to spend a lot of time when we're talking about if statements, is how to generate these Boolean results. In this case, I'm just using the literal true, which is the simplest Boolean result that we can come up with. And then inside of these curly braces here, I've got the code that's going to execute if that Boolean test returns true. So in this case, since we're using a literal true, then the test is always going to pass, and when I run this application, I see that I get this test is true printed out in the results here. If I change this to a literal false, then we see that we don't get any output from the application because the code inside of the curly braces is not executed. Now, one thing to keep in mind if you're coming to Go from another language is you may be expecting this to be valid syntax. Well, if we try and run this, we actually are going to get a syntax error because one of the design decisions that was made with Go is that you are never allowed to have a single line block evaluate as the result of an if statement. So you always have to use curly braces even if you only have one line to execute. Now this style of if statement has the Boolean test right here, and that's the only thing after the if clause. There's actually another style that's very commonly used in the Go language, and that's what I would call the initializer syntax. So as you see here on line 17, we've got a call into a map that's pulling out the value from a map and is pulling out the OK variable. And then notice I've got this semicolon and then the Boolean result listed here. So this part here, this first part of the if statement, is the initializer. So the initializer allows us to run a statement and generate some information that's going to set us up to work within the if block. So in this case, I'm generating a Boolean result by interrogating the map, and then I'm using that as the test to see if the code inside the if block should execute or not. I also have access to the pop variable that I'm creating right here inside of the if test, and that variable is going to be scoped to the block. So if I execute this, you see that I get the population of Florida printed out, no problem there. If I try and work with that variable outside of here and print it out again, I'm going to get an undefined error because the pop variable is only defined within the scope of that if statement. The next thing that I want to talk about with if statements are the comparison operators that we have. I mean, obviously, as long as we can generate pure Boolean values, things are going to be pretty simple, but that's of pretty limited benefit because in a lot of applications, we need to do some kind of a comparison in order to determine if the branch should execute or not. So let me drop in this example here, and let's just say that we're building some kind of a number guessing game. Now, to keep things as simple as possible, this is going to be a pretty simple number guessing game because we're going to hard code the value that we're going to guess, and we're going to hard code our guess. So we're not going to have a user interface involved here at all, and we're not going to randomly generate the number. That way it's very clear what the application is doing. So right now what we have is we've got the number that we're going to try and guess, we've got our guess here on line 9, and then we've got a couple of tests. So in line 10, we're checking to see if the guess is less than the number. So this is the first comparison operator that we're looking at. This is the less than operator. We also have the greater than operator and the equality operator. So if we run this with the guess of 30 and a number of 50, we're going to get the value too low printed out because this first test evaluates to true and the second and third test evaluate to false. If I change my guess to 70 and run, then the second test evaluates to true and the first and third evaluate to false. And as you might expect, if I put in a guess of 50 and run this, then I finally got it. So this is the basics of a number guessing game. All you need to do is wrap this in loops, which we'll talk about in a future video, and add a little bit of a user interface, and you've got your first game written in the Go language. Now there are some other operators that we have available, and it's a little hard to justify getting them into this example, so I'm just going to go ahead and dump them here, and then we can take a look at them. So this first test is called the less than or equal operator, so it's going to check to see if number is less than or equal to guess. The second is the greater than or equal to operator, and the third is the not equal operator. So if I go ahead and run this, you see that We are less than or equal to because we're exactly on the number. We are also greater than or equal to, and we fail the not equal to test. So we get true, true, false printed here. If we go with 30 again, we're going to get false, true, true. And if we go with 70, we're going to get true, false, true. So these are the 6 different comparison operators that you're typically going to use in your applications. And these work with all numeric types. They don't, however, work with things like string types. So if you're going to work with string types, typically what you're going to work with is the equality operator or the non-equality operator. And that goes for any kind of reference type as well. Now, the next thing that I want to do in this example is add in some kind of simple validation. So if you imagine that we've got some kind of a simple user interface where the user is asked to enter a number on the keyboard, and then we're going to use that as our guess, then we're going to need some way to validate that number to make sure that, for example, they don't enter -5. So to do that, we can add another logical test, but we can also combine multiple tests together using what are called logical operators. So let me drop this code in here, and you can see our first logical operator. So this code here is conducting 2 tests. It's checking to see if the guess is less than 1 or if the guess is greater than 100. And if it is, then we're going to print out a message here. We can also put a guard around our actual game code, checking to see if the guess is greater than or equal to 1, and this is the AND operator, less than or equal to 100. So this first test case is going to execute if the guess is out of range. So if we enter -5, for example, then we're going to run this, and we see that the guess must be within 1 and 100. If we enter a number that's within range, then everything executes like we expect it to, and this code on line 11 doesn't execute. So this first operator here is called the OR operator, and this is checking to see if the test on the left is true or the test on the right is true. So obviously we can't have the guess less than 1 and greater than 100 at the same time, but one or the other could be true, and if one of those is true, then we're going to have an invalid guess, and it makes sense to print out a message to the user saying that. This other operator that we see here is called the AND operator, and it evaluates to true if both the test on the left and the test on the right evaluate to true. So if we had a guess, for example, of 105, then this code is going to evaluate to true because it is greater than or equal to 1, but this code is not because 105 is not less than or equal to 100. So with an AND test, both cases have to be true, unlike an OR test where only one of the two has to be true. So a guess of 105 is going to print out our error message, and it is not going to execute the code within this if statement here. The other logical operator that we have is called the NOT operator, and what that's going to do is it's going to take a Boolean and it's going to flip it to the other side. So if I take, and just as a simple example, if I take and print the value true out, then we're going to get the value true printed out here at the end of our program. If I put the NOT operator, which is just an exclamation point, and run that, then the true becomes false. Similarly, if I put this in front of a false, the false becomes true, and I can just prove that false is really false by taking that away, and false is false. So those are the 3 logical operators that we have. We've got the OR operator, which is the double pipe that you see here on line 10. We've got the AND operation, which is the double ampersand, which you see here on line 13. And then we have the NOT operation, which reverses a Boolean result, and that's done simply using the exclamation point. The other interesting thing to know about working with logical operators is a concept called short-circuiting. So in order to show you that, I'm actually going to have to jump ahead and add a custom function here, and we haven't talked about this, so let me just give you as simple of an explanation as possible. So I've got a function down here between line 27 and 30 called return true that's going to return a Boolean result. Now in order to make sure that we know that it executed, I'm printing out returning true here, and then I am returning the true value. So what happens when we call this function is it's just going to be replaced with the Boolean true in our application code. Now up here in line 10, I've changed our OR test to include this return true. Now this doesn't make sense in our demo example, but I'm doing this just to show you how this works. So in this case, we're ORing 3 tests together. So what's going to happen is Go is going to evaluate these guys, it's going to generate a result, and it's going to take that result and it's going to OR it against this guy. So basically it's going to evaluate all of them, and only one of those has to be true in order to generate a validation message. So as you might expect, if we run this like this, we're going to get returning true because the guess is not less than 1. So we're going to check this value, this returns true, and so we're going to evaluate if it's greater than 100. None of those are true, so our OR statement fails, and then we're going to drop down and we're going to execute this code down here like we might expect. If we generate an invalid value, so if we put a -5, then, well, let's just run it and we'll see what happens. So if we run this, we get the validation message. The guess must be within 1 in 100. Well, that's okay, but what happened to our return true? If you remember, this function is supposed to print returning true out, and it didn't. So what happened? Well, what happened is a concept called short-circuiting. So as soon as one part of an OR test returns true, then Go doesn't need to execute any more code. It already knows that the OR test is going to pass. So it does what's called short-circuiting, which basically means it's not going to evaluate any other part of the OR test. It's just going to move on and say, well, the OR test passed, and therefore everything works. So in this case, since guess is less than 1, there's no reason for Go to evaluate these two tests here. So since this test is a function call, it doesn't even execute that function. Now, if we go the other way and we go out of range high, then this is going to return false. This is actually going to return true because it's hard-coded, and actually Go isn't even going to evaluate this because this is going to return true. However, this value is going to fail this test here. So if we run this, we see that now we get returning true printed out. So this is a concept called short-circuiting. Go is going to lazily evaluate the logical tests that we put in here. So when we give it -5, since it doesn't need to evaluate anything after this first test, it doesn't. So any function executions are not going to be evaluated. The same thing happens for an AND test. If one of the parameters returns false, then we're going to get a short-circuiting here. So if we get into a situation where this is false, Go will not even evaluate this test here. So for example, with the -5, when Go evaluates this, it sees that the guess is not greater than or equal to 1, so the AND test has to fail because both sides of an AND test have to return true in order to work, and so Go is going to exit early and it's not going to execute this code. So for the next thing that I want to talk about, I want to actually drop back into our baseline for our test here. And I want to talk a little bit about these two if tests. Now this code obviously works, but it's a little bit ugly, right? Because we have this logic here, guess is less than 1 or guess is greater than 100, and then we have this expression here, and this is exactly the opposite. So this is basically saying, well, if it's not less than 1 or greater than 100, then do this other thing. So while this code is perfectly fine, it becomes a little bit of a maintenance nightmare because really our intent is that we want to execute either this code or this code. So the way we can do that a little bit more elegantly in Go is by taking out all of this and just putting in the keyword else. So what's going to happen in this situation is it's going to evaluate the logical tests. If these tests return a Boolean true, then we're going to print this. Otherwise, we're going to execute this block here. So in this case, if we run this, we see that we get the value too low, and our logical tests down here on line 21 execute. If we put in the value -5, however, then we get the same behavior that we had before, but our code is a lot cleaner and a lot more clear as to our intent. Now related to that is the situation where we have multiple tests that we want to chain together. So let me paste in another permutation of our little game. And in this case, I've actually split out the validation logic. So I want to check if it's less than 1, I want to print out one message. If it's greater than 100, I want to print out another message. Otherwise, I've got a valid value. And to do that, I'm using this else if clause. So basically what this is doing is it's taking an if test, and then it's chaining on another if test if this fails. And so what Go is going to do is the first logical test that passes is going to be executed. Otherwise, it's going to drop down to the else clause. So with the guess of 30, we would expect our else clause to fire. So if we run, we see that in fact it does. If we put in a value of -5, then we would expect this first statement to run, and it does. And if we put in a value that's too high, then we see that we get the second validation message printed out. And those are the three different ways that we have to create if statements. So we've got the simple if statement that's just if, and if that evaluates to true, then the statements inside of the curly braces are going to execute. We've got if else, so we're either going to execute the first set of code or the second set of code. And then we have the if else if, which we can chain together with else in order to have very complicated branching so that we can have multiple code paths execute depending on how our logical tests execute. Now one thing to keep in mind is through these examples we've never been able to have more than one code path execute. So even if we did something like this, if we did else if guess is less than 1 or, then notice both the first test and the second test will pass with a value of -5. However, Go is only going to execute the first branch that has a succeeding test. So we get the result, the guess must be greater than 1 because this test passed, and so this test wasn't even evaluated. Go immediately went in and executed this branch of code and ignored all of the rest of our if statements. Now, another thing to keep in mind when you're working with equality operators, and this isn't specific to if checks, but it is something that's easy to demonstrate with an if check. So if I take a look at this example here, I've got a floating point number of 0.1, and I'm going to check to see if that number is equal to the number squared, and then I'm going to take the square root of it. So if you get out a pencil and paper, you're going to take 0.1 squared, which is going to be 0.01, and then you're going to take the square root of that, which is going to be back to 0.1, right? So this should evaluate to true. If we run this, we see that in fact they are. However, if I add in a couple of decimal places here and run this, now Go says the results are different. Well, the fact is that if you square a number and take the square root of it, it is the same number. So what's going on here? Well, the thing is, Go is working with floating point numbers, and floating point numbers are approximations of decimal values. They are not exact representations of decimal values, and so we have to be very careful with them. So when we're doing comparison operations with decimal values, this is generally not a good idea. The better approach is to generate some kind of an error value and then check to see if that error value is less than a certain threshold. So in this case, since we're taking a floating point number and comparing it to a floating point number, what we can actually do is divide the two numbers and subtract 1, and now what we have is a value that's close to 0. So if we take the absolute value of that, so we'll use the ABS function which does that from the math package, and then check that to see if it's less than, for example, 0.001. What this is doing is saying divide these two numbers, and if they're within 0.1% of each other, then we're going to consider them to be the same. So if we run this, then you see that the results are the same, and we can add as many decimal places as we want right now, and the errors that are associated with floating point numbers aren't going to get in our way. Now, this isn't a perfect solution because you could get two numbers that aren't truly the same and get them to pass this test. So the key to that is tuning this error parameter here, making sure that it's sufficiently small to catch those cases, but sufficiently large so that the errors introduced with floating point operations don't affect your results. Okay, so the next thing that I want to talk about are switch statements. So let me start that conversation by dropping in an example, and we'll see a basic switch statement. So a switch statement is a kind of special purpose if statement. So where an if statement has a logical test and runs a block of code if that test is true, and then you can add an else if to run a second test and another else if and as many else ifs as you want. A lot of times in application development, we run into a set of comparison operations that are very similar to one another. So a lot of times it's more efficient to use a switch instead of an if statement. So we have a simple example here. We're going to use the switch keyword, as you might expect. And in this example, we're going to start with this value here, and that's called a tag when we're working with switch statements. So this is what we're going to compare everything against. Then we're going to have a series of cases, and you see here we got case 1 and we got case 2. So what's going to happen is the value here is going to be compared to the tag. And if it's true, then the statements after the case are going to execute. If not, then they're not going to execute. And just like with if statements, the first case that passes is going to be the one that executes. We also have this default case down here, and that's going to execute if none of our other test cases pass. So if we go ahead and run this, we see that we get 2 printed out. If we add the value 1 here, we get the value 1 printed out. And if we have 3, then we get the default case printed out. So it's a very simple way to compare one variable to multiple possible values for that variable. Now, in a lot of languages, if you want to compare against a range, then you'd have to do something like this. You'd have case 2, you'd have case 3, and then we use what's called falling through in order to compare multiple cases together. Well, we don't actually have falling through as a default behavior in Go, but what we do have to make up for that is the ability to have multiple tests in a single case. So if I extend this example out here, and I say that this is going to test 1, 5, and 10, and this is going to test 2, 4, and 6, then I'm going to say this is going to print out 1, 5, or 10, and this will print 2, 4, or 6. And then I put in the value 5, and let's just change this message to, this is going to say another number. Okay, so if I run this, then I get the first case is going to pass because I matched this second test. So this is going to execute if I have the value 1, 5, or 10. So I can also get into that same case by passing in the value of 1. If I pass in the value of 4, then like you might expect, I'm going to have the second case evaluate. And naturally, if I pass in an unknown number, then I'm going to have the default case execute just like I had before with a single test. Now, one thing we have to be aware of is the test cases do have to be unique. So if I try and run this, where I'm going to have 5 in the first case and in the second case, that's actually a syntax error because you can't have overlapping cases when you're using this syntax. Now, just like with if statements, we don't have to have a simple tag here. In our switch, we can use an initializer, just like you're seeing here. Now, in this case, the initializer doesn't have to generate a Boolean result because we're not doing a Boolean test in our switch statement up here. The Boolean test is comparing the second parameter in the switch statement to our cases. So in this case, we're just going to initialize that value. So I'm doing some simple math here. I is set equal to 2 plus 3, so obviously that's going to be 5. Then I've got the semicolon and the tag that we're going to be testing against. So as you might expect, when I run this, the first case executes because 2 plus 3 is 5. 5 is matched by the first case, and so we get this statement printed out. Now, another syntax that we have available to us in switch statements is a tagless syntax. So both of the styles that we've been talking about, we've always had a value that we're comparing to our test cases. Well, there's actually another syntax, this tagless syntax, and this is arguably more powerful than the tag syntax, although it is a little bit more verbose. So in this case, on line 8, I'm establishing a variable, which is going to come from some other logic in my application. And then I've got the switch statement that's standing all alone and immediately opening a curly brace. So notice I don't have a tag here. However, in my case statements, now I've got full comparison operations. And I can use the comparison operators, I can use the logical operators. So in this case, the cases are standing in for the logical tests that we have in our if statements. They're doing exactly the same job. So in our first case, I'm checking if I is less than or equal to 10. And if it is, then I'm going to print that out. And then in our second case, I'm going to check if I is less than or equal to 20. And then, of course, we've got the default case if the value falls through. So if I run this, I see that I do get the code executing, which is an interesting thing, and it executes the first case. Now, why is this interesting? Well, if you notice, the first case and the second case overlap. Because 10 is less than or equal to 10, it's also less than or equal to 20. So unlike the tag syntax where I've got multiple test cases and I said they cannot overlap, when we're using this tagless syntax, they are allowed to overlap, and if they do, then the first case that evaluates to true is going to execute. Now, another thing that I should have pointed out earlier is notice that we don't have curly braces around this. Any statement that's after this case and before the next case is going to be part of the block that's going to execute. So I can have as many statements as I want here. The delimiters in this case are the actual case keywords, the default keyword, or the closing brace. So any of those delimit the end of a block in a case statement. Now again, if you're coming from another language, then this syntax might be looking a little weird because you might be looking for this word coming in here, and we'll have to add this word here, and we'll have to add this word here. So you might be wondering, where the heck are my break keywords? Well, in Go, the break keyword is actually implied because so many use cases for switches have breaks in there, and forgetting a break is the cause of innumerable errors when working with switch statements. The design decision was made to have an implicit break between our cases instead of an implicit fall through, which most other C-based languages have. So, what happens if you do in fact want your case to fall through? So in this example, let's just say that we do want to print out that we're less than or equal to 10 and that we're less than or equal to 20, and we know that if we pass this first case, we're going to pass this second case too. In that case, we can actually use the keyword fall through. So if I run this, you see that both messages print out. So I'm going to get less than or equal to 10 and less than or equal to 20. Now, one thing to keep in mind here is fall through is logicless. So when we say fall through to the next case, it will do that. So if I, for example, change this to be greater than or equal to, then we know that I fails this second case. But if I run, it still executes because fall through means that you are taking the responsibility with the control flow and you intentionally want the statements in the next case to execute. Now in Go, you don't use fall through very often because we have that tag syntax that can take multiple tests per case, and so a lot of the use cases for falling through are taking care of that. However, if you do have a use case where you need fall through, then it is available to you. The next thing that I want to talk about with switch statements are a special use of a switch statement called a type switch. So I'm going to drop in this example here, and this should be pretty familiar except for what we're switching on. So notice that we are switching on a tag, but the tag variable is typed to type interface. which can take any type of data that we have in a Go application. So the interface type can be assigned to an integer like we're seeing here. We can assign it to a string, to a boolean, to a function, to a struct, to a collection. Anything we want to assign to an interface is going to be permissible. So then in Go, we can use this syntax here. So we can put in the dot operator, and after that, put in parens with the word type in the middle. And what that's going to do is tell Go to pull the actual underlying type of that interface and use that for whatever we're doing next. Now, you don't just use that for type switching, but this is a common use case for it. So in this case, I'm going to assign the variable I the value 1, which, as we know, is going to type I to be an integer. And then I can actually use Go types as the cases. Because this is going to return a type, then I can use those type keywords here as my cases. So if I run this, knowing that 1 is an integer, I should not be surprised when I see the first case passes and the other two are ignored. If I add a decimal point 0 here, then that's going to turn this into a floating point 64, and we see that Go recognizes that. Similarly, if I put 1 in a string here, then we're going to see that Go understands that. And I can even make, for example, an array, and we don't need to initialize any values here, but if we see that, then Go recognizes that as another type. And if I want to have a case to catch that, then I can actually have a case for arrays of 3 integers, and then I can print that out. Now if I run, we see that it recognized that. And this is different than 2. So if I use a 2-element array, please be aware that those are different types. Arrays are not equivalent to every other array. You have to have the same data type and the same array size in order for them to be evaluated as the same type. Okay, the last thing that I want to talk about, I can illustrate with this example here. Now in this example, we're extending on the previous one with type switches, and notice that I've got these two print statements here on line 11 and line 12. So if I run this, I see that I is an integer, and this will print 2. Well, in some situations, you might need to leave a case early. So maybe inside of the case, you're executing some kind of a logical test, and you find out that there is some logic in the case that you don't want to execute in certain situations. Well, if you want to do that, you can actually exit out of the switch statement early by using the break keyword. So if I add that and run, then I have a way to break out of the switch early, and I'm not going to execute any code below that break statement. So you could wrap this in a logical test to determine if you've got a validation error, for example, on some incoming data. You might not want to save that data to the database, and then you can use this break keyword in order to short circuit that save operation. Okay, so that pretty much wraps up what I have to talk about with if and switch statements. Let's go into a summary and review what we've talked about. In this video, we started our discussion about the different control flow tools that we have available to use in our Go applications. And we started out by talking about the very basic if statements and how we can use a Boolean variable to determine if a block of statements will execute or not. We then talked about the initializer syntax and how that allows us to execute a statement that's going to set up variables that we can use to run our test against, as well as use within the statements of our if tests. We then talked about the comparison operators, and we talked about how there are 6 of them. We've got less than, greater than, less than or equal to, and greater than or equal to work with primarily the numeric types, as well as the double equals operator and the not equals operator that are available to be used more generally. We talked about the logical operators, the AND operator, the OR operator, and the NOT operator that allow us to chain together Boolean operations, as well as reverse the result of a Boolean operation in the case of that NOT operator. We talked about short circuiting and how when you're chaining together tests with an OR operation, for example, if any one of those logical tests evaluates to true, then the remaining tests are not executed. So any side effects or any functional operations that might occur with those are not going to be executed. Similarly, with an AND test, the first part of an AND test to return a false result is going to halt the execution of that AND test. So any side effects you might be relying on afterward are not going to occur. We then talked about the 2 different variants of if tests. We talked about the if-else statement and how we can use that to execute one of 2 branches of code. So if the if test succeeds, then we're going to execute the first block of statements. Otherwise, we're going to execute the second block of statements. Related to that is the if-else if statement. And in this case, instead of determining between one of 2 paths and forcing your code to execute one of those, you can add additional logical tests. So at most, one block is going to execute. But if all of your if tests fail, then you might not get any blocks executing. And finally, I took a minute to talk about equality operations, especially when working with floating point numbers, and how equality and floats don't really get along that well. So if you do need to do some kind of an equality operation with floating point numbers, then you're going to want to turn that into some kind of a comparison operation against an error function. So for example, we were checking to see if two floats were equal. Instead of checking to see if they're actually equal, we divided them, subtracted 1 from that result, and checked that against an error parameter. So we decided if they were within 0.1%, they were going to be considered the same. You can use a similar type of error function with your operations, but in general, you should not test to see if two floating point numbers are equivalent to one another. We then moved on to talk about switch statements and the various ways that we can use those in our applications. We started by talking about how to switch on a tag, where a tag is just another name for a variable, but that variable has a special significance in a switch statement because all of your test cases are going to be compared back to that tag. We talked about how with Go we can have multiple tests with our case statements, and by doing that we can actually eliminate a lot of situations in other languages where we need to fall through and chain multiple cases together. Well, in Go, we can just add those multiple tests in the same case and eliminate the need to do that falling through. We also do have initializers available with switch statements, but instead of the initializer generally generating a Boolean, as we do with an if statement, the initializer is going to generate the tag that's going to be used for the comparisons in our cases. We talked about switches with no tags and how it adds a lot of flexibility to the switch statement, but it is a little bit more verbose syntax. So instead of the cases being compared for equivalency with the tag, we're going to actually put in the comparison operation ourselves so we can use more than just equivalency testing. We can check less than or equal to or any other comparison function, including chaining comparisons together by using logical operators. We talk about how we have the fall through keyword available in switches and how that replaces the break keyword in many languages. So where many languages have implicit fall through and explicit breaking, in Go, we flip it around. So we have implicit breaks, but if you do need one case to fall through to the next, then you can use this fall through keyword. Now, one thing to keep in mind when you're doing that is when you're falling through, any additional case logic is not executed. The fall through will override any case logic that you have, and so the next statements will execute regardless of if that case would normally pass or not. We also talked about type switches and how we can use that special syntax by adding a dot paren type paren on an empty interface in order to get the underlying type of that empty interface. So for example, if we've got an empty interface that's holding an integer, then we can use that syntax in order to get that underlying integer value. Then in our switches, we can switch against those types, and then we can make a decision based on the data that we got in. And finally, we talked about breaking out early. When we've passed into a case in our switch statement, there are times when in the middle of the case we need to exit out early because we've done some additional analysis and we've decided that we should not proceed executing this case. So for example, we've got a switch statement, and inside of that case, we're doing some validation on the data before we save it to the database. We might decide that data is invalid and we should not proceed to save it to the database. So in that case, you can use the break keyword, break out of the case, and continue execution after the switch statement.